Hello there, and welcome to Science for Sleep, the quiet little corner of the universe where enormous cosmic mysteries drift by slowly enough for us to enjoy them without needing to pass an exam afterward. Tonight, we are travelling very far from Earth, beyond our own galaxy, past clouds of ancient stars and silent stretches of intergalactic dark, towards something violent enough to tear apart entire solar systems and bright enough to outshine regions thousands of times larger than our own stellar neighbourhood. And strangely, despite all that chaos, it is also beautiful. Tonight's journey is about the Tarantula Nebula, one of the most extreme star-forming regions ever observed. A place where stars are born in numbers so large and with such intensity that astronomers sometimes compare it to the conditions of the early universe itself. It is a giant web of gas, radiation, dust, stellar winds and explosions, hanging inside a nearby dwarf galaxy like a glowing storm suspended in the dark. Now, the name Tarantula Nebula sounds slightly unfair to anyone with arachnophobia. Fortunately, the nebula is around 160,000 light-years away, which is comfortably beyond the recommended safe distance for spiders. No matter how large the Tarantula Nebula may appear in telescope images, it will not be crawling onto your ceiling tonight, at least not according to current astrophysics. Still, it does resemble a spider in a way. Long glowing filaments stretch outward from a blazing centre, like cosmic legs spreading across space. Bright clouds twist around cavities carved by radiation and stellar winds. Dense knots of gas sit hidden inside darker regions, quietly preparing future generations of stars while older stars erupt violently nearby. It is not calm there. The Tarantula Nebula is one of the loudest neighbourhoods in the nearby cosmos, if space had air to carry sound. Massive stars roar with energy, shockwaves crash through clouds of hydrogen, supernovas erupt, radiation floods entire regions with ultraviolet light, powerful enough to strip atoms apart. And in the middle of all this destruction, new stars continue forming anyway. Actually not just forming, thriving. That is part of what makes the Tarantula Nebula so fascinating to astronomers. It is not simply a cloud floating in space, it is a factory. An enormous stellar production site operating at a scale difficult for the human brain to comfortably picture. While our Sun formed in a relatively modest stellar nursery billions of years ago, the Tarantula Nebula produces stars with startling aggression. Some are dozens or even hundreds of times more massive than the Sun. Others burn so brightly that they lose enormous amounts of matter almost as soon as they're born. Some scientists believe regions like this may resemble the conditions under which the earliest galaxies in the universe formed stars. In other words, when astronomers study the Tarantula Nebula, they're not only observing an unusual cloud nearby, they may also be peeking backward into cosmic history, toward an era when the universe itself was young, crowded, turbulent, and overflowing with raw material for stars. Before we continue drifting into this glowing chaos, though, I would love to ask you something gentle and simple. Where in the world are you listening from tonight, and what time is it there right now? Perhaps it is late evening, and rain is tapping softly against the window. Maybe it is early morning and the sky outside is only beginning to brighten. Somewhere on Earth, someone is listening while wrapped in blankets. Somewhere else, another person is probably trying very hard not to fall asleep while pretending to finish work. Time zones are funny that way. Human beings spread across an entire planet, all arriving together in this quiet little moment to think about stars exploding inside a nebula shaped vaguely like a spider. That alone feels rather unlikely. And if you find this journey relaxing, comforting, or simply interesting enough to spend part of your evening with, I'd be very grateful if you liked the video and subscribe to the channel. It helps this sleepy little project continue drifting through the algorithm, instead of vanishing into the digital void where abandoned gym memberships and unfinished online courses quietly go to rest. Now then, let us move farther outward. The Tarantula Nebula does not live inside the Milky Way. That surprises many people at first because it appears prominently in astronomical photography and is often discussed alongside famous nebulae from our own galaxy. But technically, this enormous structure belongs to one of the Milky Way's neighbouring galaxies, a dwarf galaxy called the Large Magellanic Cloud. Despite the name, the Large Magellanic Cloud is not actually a cloud in the weather sense. No rainstorms, no lightning, no dramatic weather presenters gesturing at maps. It is a small satellite galaxy orbiting the Milky Way, visible primarily from the southern hemisphere. Ancient observers saw it long before telescopes existed, appearing as a hazy patch in the night sky. Sailors navigating southern oceans centuries ago noticed it glowing faintly overhead, long before anyone understood what it truly was. Inside that neighbouring galaxy, the Tarantula Nebula burns with astonishing brightness. If it were as close to Earth as the Orion Nebula, it would cast visible shadows at night. Think about that for a moment. A nebula bright enough to create shadows. Not a star, not the moon, a cloud of glowing gas. The scale is difficult to overstate. The nebula stretches across roughly 1,000 light-years. That means light itself, moving at nearly 300,000 kilometers per second, would still require a millennium to cross from one side to the other. Human civilizations rise and fall in less time than it takes light to travel across this single cosmic structure. And yet, despite its immense size, the Tarantula Nebula is still only one region within one small neighbouring galaxy, among trillions of galaxies spread across the observable universe. Astronomy has a way of making human arguments feel oddly temporary. Somewhere out there, giant stars are detonating with energies beyond comprehension, while humans on Earth continue debating whether pineapple belongs on pizza. The universe contains multitudes. At the centre of the Tarantula Nebula lies an especially intense cluster called R136. We will eventually spend much more time there because it contains some of the most massive stars ever discovered. These stars are so extreme that astronomers initially struggled to believe their measurements were correct. Normally, stars above a certain mass should become unstable. Physics places limits on how large stars are expected to grow before radiation pressure begins tearing them apart. Yet inside R136, nature appears to have pushed frighteningly close to those limits anyway. Some stars there may have formed with masses over 200 times greater than the Sun. To put that in perspective, our Sun already contains more than 99% of all the mass in the solar system. Jupiter, despite being enormous compared to Earth, is still tiny beside it. Now imagine something 200 times more massive than the Sun itself. These stars are not merely large, they're almost absurdly energetic. And because massive stars burn through fuel quickly, their lives are short. A star like our Sun may survive roughly 10 billion years. Some of the giants inside the Tarantula Nebula may only live a few million years before collapsing or exploding. In stellar terms, they are cosmic mayflies, brief, furious bursts of light. That creates an interesting contradiction at the heart of the nebula. The same stars responsible for illuminating the region are also slowly destroying it. Their ultraviolet radiation blasts surrounding gas apart. Their stellar winds carve cavities into nearby clouds. Eventually, many will explode as supernovas, sending shockwaves tearing through space. But oddly enough, those same destructive forces may also trigger new star formation elsewhere. Compression from shockwaves can squeeze gas clouds tightly enough for gravity to take over, collapsing material into brand new stars. So the nebula exists in a constant cycle of creation and destruction. Stars form, shine, destabilize their surroundings, explode, and help produce future generations. Space is often described as empty, but regions like this feel almost alive with activity. Not alive in the biological sense, of course. The Tarantula Nebula is not thinking about anything. It has no awareness, no goals, no intentions. But it is dynamic, energetic, restless. It changes continuously over time scales both enormous and surprisingly brief. In fact, if humans could somehow observe the nebula over millions of years in fast motion, it would likely appear turbulent, and unstable. Clouds would twist, cavities would expand, new stars would ignite while older ones detonated violently. Filaments would stretch outward like smoke swirling through invisible currents. The universe, when sped up enough, stops looking static. That realization took humanity a surprisingly long time to reach. For most of history, the night sky seemed permanent. Ancient civilizations saw stars as fixed points arranged eternally overhead. The heavens appeared stable compared to Earth's unpredictable weather, wars, and changing seasons. Only gradually did humans discover that stars evolve, galaxies move, and nebulae transform over time. Even our own sun is temporary. One day, billions of years from now, it too will swell into a red giant, altering or destroying the inner planets before ending its life as a white dwarf. The solar system itself exists inside time's long machinery. And compared to the stars inside the Tarantula Nebula, the sun is actually fairly calm. That may sound strange, considering the sun occasionally launches solar storms capable of disrupting satellites and electrical systems. But beside the giants of R136, our star resembles a quiet suburban resident living far from the cosmic city centre. Inside the Tarantula Nebula, stellar violence operates on another level entirely. Radiation there is intense enough to strip electrons from atoms across enormous distances. Stellar winds race outward at millions of kilometers per hour. Supernovas inject unimaginable amounts of energy into surrounding space. Entire regions glow because atoms are continuously being excited and ionized by nearby stars. And despite all this violence, astronomers love studying it. Partly because the nebula is beautiful, of course. Telescope images reveal brilliant reds, blues, purples and golds woven through dark structures of dust. The shapes appear organic, almost biological, even though they emerge from pure physics acting over immense scales. But scientists are interested for another reason too. The Tarantula Nebula may help answer one of astronomy's biggest questions. How did the first generations of stars and galaxies evolve after the Big Bang? The early universe likely experienced periods of rapid star formation far more intense than what we see in most nearby galaxies today. But those ancient galaxies are incredibly distant and difficult to observe clearly. The Tarantula Nebula offers a closer laboratory where astronomers can examine similar processes happening in relative detail. In other words, this violent cloud may serve as a nearby stand-in for conditions from billions of years ago, which is slightly amusing when you think about it. Human beings built delicate telescopes on a small rocky planet orbiting an average star inside one galaxy, so they could study a glowing storm in another galaxy to understand what happened near the beginning of time itself. That is either extremely impressive or a clear sign humans are constitutionally incapable of minding their own business on a cosmic scale. Probably both. As telescope technology improved, especially with instruments like the Hubble Space Telescope and later the James Webb Space Telescope, the Tarantula Nebula revealed more and more complexity. Structures once blurred became sharp. Hidden stars emerged through dust. Entire populations of young stars appeared inside previously dark regions. And the more astronomers observed, the stranger the nebula became. Because it turns out the Tarantula Nebula is not merely producing stars efficiently, it is producing them in clusters so dense and energetic that they reshape their entire environment almost immediately after birth. Imagine a city where every newborn arrived driving a bulldozer while setting off fireworks and hurricane-force winds simultaneously. That would still undersell the situation somewhat. Yet somehow, amid all this apparent disorder, gravity continues assembling new stars from collapsing gas clouds. The process never fully stops. The nebula remains active, continuously recycling matter through different stages of stellar life and death. Long before astronomers understood what the Tarantula Nebula truly was, people simply saw a faint glowing patch hanging in the southern night sky. Not a star exactly, not a planet, just a hazy smear of light sitting quietly beyond the familiar constellations if you had travelled through the southern hemisphere centuries ago, perhaps aboard a wooden sailing ship crossing dark oceans beneath clear skies. You might have noticed it too. Far from city lights and electric glow, the sky would have appeared impossibly crowded with stars. The Milky Way itself would stretch overhead like spilled silver dust, bright enough to cast a faint shadow under perfect conditions. And somewhere nearby, floating almost unnoticed beside that river of stars, sat two mysterious cloudy shapes. Today we call them the Large and Small Magellanic Clouds. Back then nobody knew they were galaxies. In fairness, humanity did not even know our own galaxy was a galaxy yet. For most of history, the Milky Way was simply thought to be a band of light wrapped around Earth's sky. Ancient observers interpreted the heavens through mythology, religion, navigation, and storytelling. The idea that the universe contained billions of galaxies separated by incomprehensible distances would have sounded less like science and more like someone becoming extremely philosophical after not sleeping for 3 days. The Large Magellanic Cloud, where the Tarantula Nebula lives, appeared strange even to early sky watchers because it did not behave like ordinary stars. Stars remained sharp points of light. Planets wandered slowly through the sky, but these cloudy patches stayed diffuse and unchanged. Some cultures viewed them as celestial rivers or campfires in the heavens. Others incorporated them into navigation traditions. Polynesian navigators, for instance, possessed extraordinary knowledge of the southern sky long before European exploration reached those regions. They crossed enormous stretches of ocean, guided partly by stars many northern civilizations had never even seen. Meanwhile, in Europe, awareness of the Magellanic Clouds spread more widely during the Age of Exploration. The clouds eventually became associated with the Portuguese explorer Ferdinand Magellan after his expedition circumnavigated the globe in the early 1500s. To be clear, Magellan did not discover them. Millions of people living in the southern hemisphere were probably quite surprised to hear somebody else had apparently found the glowing objects already hanging above their heads. Still, the name stuck, and inside the Large Magellanic Cloud, hidden within that faint celestial patch, sat one of the most violent star-forming regions in the nearby universe, the Tarantula Nebula. At a distance of roughly 160,000 light-years from Earth, it is technically not very far away by galactic standards. That phrase sounds ridiculous in ordinary life, of course. If somebody described a grocery store as not very far away, and it required 160,000 years for light to reach it, you would probably consider shopping elsewhere. But astronomy changes perspective. The Milky Way itself spans around 100,000 light-years. The Andromeda Galaxy, our nearest major galactic neighbour, sits over 2.5 million light-years away. Compared to much of the observable universe, the Large Magellanic Cloud is practically living next door. And that proximity matters enormously. Because the Tarantula Nebula is so bright and relatively nearby, astronomers can study it in extraordinary detail. If it were much farther away, many of its smaller structures would blur together into a single glowing patch. Instead, modern telescopes can peer deep into its tangled clouds, revealing clusters of young stars, dense pillars of gas, expanding shock fronts, and cavities carved by radiation. In some ways, the Tarantula Nebula became astronomy's perfect laboratory. Violent enough to resemble the giant starburst regions of the early universe, yet close enough for humans to study carefully. That combination is rare. Most nearby nebulae inside the Milky Way are calmer and smaller. The famous Orion Nebula, for example, is an active stellar nursery and absolutely fascinating in its own right, but it is comparatively modest. The Tarantula Nebula produces stars at a rate so intense that it behaves almost like a miniature galactic starburst region all by itself, and despite its enormous size, the nebula remained poorly understood for a surprisingly long time. Part of the problem involved distance itself. Human brains evolved to throw rocks accurately and avoid predators hiding in bushes. They did not evolve to intuitively process cosmic scales. Even today, most people hear light year and mentally translate it into very far, which is understandable because the actual numbers become absurd very quickly. A light year is the distance light travels in 1 year, moving at roughly 300,000 kilometers every second. Every second. By the time you finish blinking, light has already circled Earth multiple times, and yet even at that speed, light from the Tarantula Nebula requires 160,000 years to reach us. Which means when you look at it through a telescope, you are not seeing the nebula as it exists now. You're seeing ancient light that left long before human civilization developed agriculture. At the time that light began its journey, mammoths still walked across parts of Earth. Astronomy is deeply strange that way. Telescopes function partly as time machines. Every distant object appears as it existed in the past, because light requires time to travel. The farther away something is, the older the image we receive. So when astronomers study the Tarantula Nebula tonight, they're observing a version of it from roughly 160,000 years ago. Perhaps some of the stars visible there no longer exist. Massive stars live fast and die young. Some may already have exploded as supernovas long before humanity built its first cities. We simply have not seen those explosions yet. The universe keeps secrets temporarily hidden behind the speed of light. And speaking of visibility, the Tarantula Nebula itself cannot usually be seen clearly with the naked eye as an individual structure, though the Large Magellanic Cloud can appear visible under dark southern skies. Through telescopes, however, the nebula becomes extraordinary. Early astronomers observing it through increasingly powerful instruments noticed a chaotic glowing region, unlike ordinary star clusters. Its filaments and bright central areas appeared tangled and irregular. Over time, improved observations revealed a sprawling network of gas and stars resembling a giant spider, hence the name. Although depending on the telescope image, it sometimes resembles a crab, roots, smoke, lightning, or spilled paint. Humans are excellent at seeing familiar shapes in random patterns. Give us enough glowing gas clouds and eventually somebody will point at one and say, "That one looks slightly like a household pest." To be fair, NGC 2070, one of the nebula's catalogue designations, is considerably less memorable than Tarantula Nebula. Astronomers do wonderful work, but naming conventions occasionally sound like malfunctioning printer serial numbers. Still, behind the dramatic nickname lies something genuinely astonishing. The Tarantula Nebula is the brightest known star-forming region in the entire local group of galaxies. The collection of nearby galaxies including the Milky Way, Andromeda, and dozens of smaller companions. It radiates immense amounts of energy, because thousands upon thousands of stars are forming or already burning inside it, and many of those stars are enormous, not merely larger than Earth, not merely larger than Jupiter, larger than the Sun by factors almost difficult to imagine. These giant stars flood the nebula with ultraviolet radiation powerful enough to ionize hydrogen gas across huge distances. Ionized hydrogen glows brightly red in astronomical images, producing much of the nebula's famous appearance. What we see is essentially a gigantic cloud being energized continuously by its own stars. The process resembles a cosmic feedback loop. Gas collapses under gravity to form stars. Those stars emit radiation and stellar winds. The surrounding gas heats up, glows, and shifts. Shock waves compress neighboring regions. More stars form. Some massive stars explode. The cycle continues, and because the Tarantula Nebula contains so much raw material, this process unfolds on extraordinary scales. The Large Magellanic Cloud itself contributes to the situation in interesting ways. Compared to the Milky Way, it contains lower amounts of heavier elements. Astronomers refer to all elements heavier than hydrogen and helium as metals, which sounds slightly insulting to oxygen and carbon, but makes sense in astrophysics terminology. This lower metallicity changes how stars form and evolve. Early in the universe, shortly after the Big Bang, almost all matter consisted primarily of hydrogen and helium. Heavier elements only formed later inside stars and supernovas. Because the Large Magellanic Cloud contains relatively low metallicity compared to regions of the Milky Way, it provides astronomers with a partial glimpse into conditions resembling earlier cosmic history. In simple terms, studying the Tarantula Nebula may help scientists understand how stars behaved billions of years ago when galaxies were younger and chemically simpler. Which means this glowing spider-shaped cloud became unexpectedly important. Not merely beautiful, not merely dramatic, important. Astronomers began focusing intense attention on the nebula during the 20th century as telescope technology improved. Ground-based observatories revealed increasing detail, but Earth's atmosphere still blurred images slightly. Then came space telescopes, and suddenly the Tarantula Nebula transformed from an interesting object into a breathtaking one. The Hubble Space Telescope captured images so sharp and intricate that entire generations of people became familiar with the nebula's appearance, even without studying astronomy professionally. Bright cavities stretched across enormous distances. Pillars of dust rose through glowing gas. Dense star clusters shone from within turbulent clouds. The nebula looked almost alive. Again, not biologically alive, obviously. It was not planning anything. The Tarantula Nebula does not wake up each morning deciding to manufacture terrifying stars for dramatic effect. But visually, it possessed movement and structure, unlike the empty darkness people often imagine when thinking about space. That misunderstanding is common. Many people picture the universe as mostly static and silent, with occasional stars scattered around. In reality, regions like the Tarantula Nebula are dynamic environments shaped continuously by gravity, radiation, magnetism, shock waves, and stellar death. If humans could observe the nebula across millions of years in accelerated motion, it would likely appear turbulent and unstable. Clouds would ripple outward, bright regions would pulse and expand, supernovas would erupt like brief flashes, new stars would emerge from collapsing knots of gas while others vanished. Space only looks still, because humans live such short lives. Even mountains on Earth change dramatically given enough time. Rivers carve valleys, continents drift, glaciers reshape landscapes. The cosmos operates similarly, just on scales far beyond ordinary human intuition. One especially fascinating aspect of the Tarantula Nebula is how visible it would appear if relocated closer to Earth. Astronomers sometimes mention that if the nebula occupied the same distance as the Orion Nebula, roughly 1,300 light-years away instead of 160,000, it would dominate the sky. It could cast shadows bright enough to see at night. Imagine stepping outside after sunset and finding an enormous glowing web spread across part of the heavens, bright enough to illuminate the landscape faintly beneath it. Ancient civilizations would almost certainly have built entire mythologies around such a sight. Actually, modern humans probably would too. The night sky once played a far larger role in human culture than it does today. Before electric lighting, people regularly experienced truly dark skies. The Milky Way itself appeared vivid and textured overhead. Constellations served as calendars, navigation systems, storytelling tools, and religious symbols. Today, millions of people rarely see more than a few dozen stars because of light pollution. Ironically, humanity became technologically advanced enough to study galaxies, while simultaneously making the night sky harder to see from everyday life. Still, observatories located far from cities continue examining regions like the Tarantula Nebula in remarkable detail. Radio telescopes map cold gas. Infrared telescopes peer through dust. X-ray observatories reveal violent high-energy processes invisible to ordinary light, and every wavelength tells a different part of the story. Visible light reveals glowing ionized gas. Infrared exposes hidden young stars buried inside dust clouds. X-rays uncover hot, shocked material energized by stellar winds and supernovas. Radio observations trace enormous reservoirs of hydrogen. Together, these observations gradually transform the Tarantula Nebula from a blurry celestial curiosity into one of the most intensely studied star-forming regions ever observed. And the deeper astronomers looked, the more extreme the situation became. Because near the nebula's centre lies a region so crowded with massive stars that it challenges previous assumptions about how large stars can even become. A cluster called R136, a place where stars are packed tightly together in astonishing numbers, flooding the surrounding nebula with overwhelming energy. Some of the stars there emit millions of times more light than the Sun. Others generate stellar winds so powerful they carve enormous cavities through surrounding gas clouds, and all of it exists inside this neighbouring galaxy quietly orbiting the Milky Way, while Earth continues its ordinary daily routines completely unaware. At this very moment, somewhere inside the Tarantula Nebula, radiation is blasting through hydrogen clouds. Massive stars are losing matter into space. Shock waves are travelling outward across enormous distances. New protostars are collapsing slowly under gravity. Meanwhile on Earth, somebody is probably looking in the refrigerator for snacks while holding the door open too long. The scale difference is humbling, yet perhaps that is part of why humans love astronomy so much. The universe is unimaginably vast and violent, but we can still understand pieces of it. Tiny conscious beings on one planet learned to build instruments capable of studying stellar nurseries in neighbouring galaxies. We traced the chemistry of distant gas clouds. We measured the motions of stars. We calculated ages, temperatures, masses and distances across incomprehensible voids, and all because humans kept looking upward. Most stellar nurseries in the universe are relatively quiet places. Not quiet by ordinary human standards, of course. Even calm nebulae contain collapsing gas clouds, ultraviolet radiation, turbulent magnetic fields, and newborn stars igniting nuclear fusion for the very first time. Compared to Earth, almost every region in space is operating under conditions that would instantly vaporize anything unfortunate enough to visit without proper protection. Still, by cosmic standards, many stellar nurseries are gentle. The Tarantula Nebula is not gentle, it is excessive. Astronomers sometimes use phrases like starburst activity to describe regions forming stars at unusually high rates. The Tarantula Nebula does not merely qualify for that description. It practically behaves like nature became impatient and decided to accelerate the entire process far beyond normal levels. Inside this enormous cloud, stars are born in huge clusters under conditions so energetic and crowded that the nebula resembles less of a peaceful nursery and more of an industrial furnace operating continuously for millions of years. And strangely enough, that violence is exactly why astronomers love studying it. Because regions like this reveal what happens when star formation becomes extreme. To understand why the Tarantula Nebula behaves so differently, we first need to talk about how stars normally form in the first place. Fortunately, despite the intimidating scale involved, the basic idea is surprisingly simple. Stars begin with clouds. Enormous clouds of gas and dust drifting through galaxies. Mostly hydrogen, with smaller amounts of helium and traces of heavier elements mixed in. These clouds can stretch across dozens or even hundreds of light years while remaining extraordinarily diffuse. Even dense nebulae contain matter spread so thinly that the best vacuum chambers on Earth would seem crowded by comparison. Space looks full in telescope images because the clouds are enormous, not because they are dense. Eventually something disturbs part of a cloud. Perhaps a nearby supernova sends a shock wave through it. Maybe galactic interactions compress material. Sometimes gravity simply amplifies tiny irregularities already present inside the gas. Gradually, denser regions begin pulling in more matter. gravity strengthens, material collapses inward, temperatures rise. As the cloud contracts, it spins faster, much like a figure skater pulling in their arms during a spin. Matter forms a rotating disk around a growing central core. Pressure and temperature increase until eventually hydrogen nuclei begin fusing into helium, and just like that, a star is born. At least just like that if you are comfortable, describing a process requiring hundreds of thousands or millions of years in extremely casual terms. Normally, star formation happens somewhat gradually. Clouds fragment into smaller regions. Individual stars or modest clusters emerge. Radiation from newborn stars begins dispersing surrounding gas, slowing further formation nearby. The Tarantula Nebula ignores moderation almost entirely. Instead of producing stars calmly and steadily, it creates enormous clusters packed densely with massive stars that reshape their environment almost immediately after birth. And the numbers involved are startling. The nebula contains enough material to form hundreds of thousands of stars. Some regions collapse into giant stellar clusters where stars are separated by distances far smaller than typical stellar neighborhoods. In our region of the Milky Way, stars are generally quite isolated. The nearest star system to the Sun, Alpha Centauri, sits over 4 light-years away. Inside parts of the Tarantula Nebula, stars crowd together much more tightly. Imagine replacing a quiet rural landscape with the centre of a packed city during rush hour, except every building is a giant star blasting radiation powerful enough to strip atoms apart. That density changes everything. Massive stars influence their surroundings aggressively. They emit enormous quantities of ultraviolet radiation, generate powerful stellar winds, and eventually explode as supernovas. In ordinary stellar nurseries, these effects often disrupt star formation by dispersing gas clouds before too many stars can form. But inside the Tarantula Nebula, there is simply so much material available that the process keeps going anyway. The nebula becomes self-sustaining in a sense. One generation of massive stars disrupts surrounding clouds, while simultaneously compressing neighbouring regions, triggering even more collapse and star formation elsewhere. It is less like a single nursery and more like a chain reaction spreading through an entire section of a galaxy. Astronomers believe several factors contribute to this extraordinary activity. One major reason involves sheer size. The Tarantula Nebula spans roughly 1,000 light-years and contains immense reservoirs of cold molecular gas. More raw material means more opportunities for gravity to gather matter into dense collapsing regions. The nebula is essentially operating with a gigantic fuel supply. Another factor involves its location inside the Large Magellanic Cloud. The Large Magellanic Cloud is not entirely stable itself. It interacts gravitationally with both the Milky Way and the Small Magellanic Cloud, another nearby dwarf galaxy. These gravitational interactions may stir gas inside the galaxy, compressing clouds and enhancing star formation activity. Galaxies are not isolated islands, quietly floating forever unchanged. They tug on one another constantly. Over millions and billions of years, gravity reshapes them, disturbs gas flows, and occasionally triggers massive bursts of star formation. In some ways, galaxies behave less like static objects and more like weather systems unfolding over cosmic time. The Tarantula Nebula may partly owe its existence to these larger galactic interactions. Then there is metallicity. Astronomers use that word constantly, so it deserves another quick explanation. In astrophysics, metals include basically every element heavier than hydrogen and helium. Oxygen, carbon, iron, silicon, neon, all of them count as metals, which means your body technically contains quite a lot of metal, despite probably not qualifying as industrial equipment. The Large Magellanic Cloud contains lower metallicity than many regions of the Milky Way. That influences how gas cools, collapses, and forms stars. Lower metallicity environments may allow especially massive stars to form more easily under certain conditions, and massive stars are where the Tarantula Nebula truly becomes extraordinary. Most stars in the universe are relatively small. Red dwarfs dominate stellar populations. Tiny, dim, efficient stars capable of surviving for trillions of years. The universe loves making small stars because they are stable and economical. They sip fuel slowly and persist almost indefinitely. Massive stars are different. They are inefficient, unstable, and spectacularly short-lived. A star 10 times more massive than the Sun does not simply burn 10 times brighter. Stellar brightness increases dramatically with mass. Some giant stars radiate hundreds of thousands or even millions of times more energy than the Sun. That energy output transforms their surroundings almost instantly. Ultraviolet radiation floods nearby gas clouds. Stellar winds blast outward at incredible speeds. Pressure waves ripple through surrounding material. Cavities form. Pillars emerge. Dense knots resist erosion while softer regions get carved away. The nebula becomes sculpted continuously by the stars forming inside it. And because the Tarantula Nebula forms so many massive stars at once, the cumulative effect becomes overwhelming. One giant star is influential. Thousands become catastrophic. Some stars inside the nebula emit enough radiation in a few seconds to exceed humanity's total energy consumption across all of recorded history by absurd margins. Not slightly absurd. Truly ridiculous levels of absurd. And yet these stars remain tiny points inside a much larger system. The central cluster known as R136 contains some of the most massive stars ever discovered. Many formed only a few million years ago, making them extremely young in stellar terms. Our Sun is about 4.6 billion years old. By comparison, stars inside R136 are practically newborns, still causing chaos in the delivery room, and what chaotic newborns they are. The most massive stars there possess surface temperatures exceeding 40,000 degrees Celsius. Some may originally have formed with masses over 200 times that of the Sun. Their radiation pressure is so intense that they continuously lose matter into space through stellar winds. Imagine a star shining so violently that it literally blows itself apart over time. These winds collide with surrounding gas and with winds from neighbouring stars. Shock fronts form, temperatures soar, turbulence spreads across the nebula. The entire region becomes an interconnected environment where every massive star influences everything nearby. And despite all this destruction, star formation continues. That contradiction fascinates astronomers because it reveals how resilient gravitational collapse can be under extreme conditions. The same forces threatening to disperse gas clouds may also compress other regions tightly enough to trigger new collapse. Destruction and creation become inseparable. A supernova may obliterate nearby material while simultaneously launching shockwaves that trigger future stars elsewhere. Stellar winds may erode one cloud while compressing another. Radiation may halt collapse locally, but encourage it in neighbouring regions. The nebula behaves like a giant self-modifying ecosystem driven entirely by physics. No planning, no intention, just gravity, energy and matter interacting across enormous scales. Interestingly, the Tarantula Nebula may resemble conditions common in the early universe. Astronomers studying distant young galaxies often observe intense starburst activity. Early galaxies formed stars much more rapidly than many galaxies today, but those ancient systems lie so far away that detailed observations become difficult. The Tarantula Nebula offers something incredibly valuable, a nearby example of similar physics happening close enough for careful study. In a sense, it acts as a local window into cosmic history. When scientists examine violent star formation inside the Tarantula Nebula, they may be learning how the first generations of galaxies transformed the young universe billions of years ago. That matters because massive stars shape cosmic evolution profoundly. They produce heavier elements through nuclear fusion. They enrich surrounding gas when they explode. They influence galaxy structure through radiation and stellar winds. They may even affect black hole formation on large scales, Without massive stars, the universe would remain chemically simple. No carbon, no oxygen, no iron, no planets like Earth, no biology, no sleepy humans listening to astronomy videos while trying not to think too hard about how all the calcium in their bones was forged inside ancient stars. The Tarantula Nebula therefore represents more than just a spectacular cloud. It is a giant active factory continuously reshaping matter into future generations of cosmic material, and the pace is astonishing. Some regions inside the nebula contain protostars still buried within thick cocoons of gas and dust. Others contain mature giant stars already destabilizing their surroundings. Nearby, supernova remnants reveal stars that already completed their entire lives. Multiple stages of stellar evolution exist side by side simultaneously. If humans could somehow safely travel through the nebula, the environment would appear extraordinarily hostile. Radiation levels near massive stars would prove lethal instantly. Temperatures inside ionized regions would reach thousands of degrees. Shockwaves from stellar winds would race through space at tremendous speeds, and perhaps most dangerous of all, the nebula changes continuously. Massive stars evolve rapidly. A star stable today may explode tomorrow in astronomical terms, though thankfully tomorrow here still usually means thousands or millions of years, rather than unexpectedly during your sightseeing trip. Probably. Still, the violence there operates on scales difficult to emotionally process. One supernova can briefly outshine entire galaxies. One stellar wind can carve cavities dozens of light years across. One giant cluster can transform the structure of an entire nebula, and inside the Tarantula Nebula, these events overlap continuously. The region almost feels overcrowded with energy. That overcrowding may also influence the kinds of stars forming there. Some astronomers suspect especially dense environments allow unusual interactions between forming stars and gas clouds. Collisions, mergers, and competitive accretion may all contribute to the creation of extremely massive stars. In quieter regions, stars often form relatively independently. Inside the Tarantula Nebula, everything interacts. Gravity from neighbouring stars disturbs gas flows. Radiation alters cloud temperatures. Shock waves compress and disrupt material simultaneously. The environment becomes intensely interconnected. It is cosmic urbanization on a terrifying scale, and despite decades of study, astronomers still debate important details about exactly how such massive stars form in the first place. Because there may actually be upper limits to stellar size imposed by radiation pressure. At some point, growing stars become so luminous that their outgoing radiation should push surrounding gas away faster than gravity can pull it inward. Yet somehow, nature occasionally produces stars near or beyond those expected limits anyway. The Tarantula Nebula contains some of the best evidence for these extreme stellar giants, which means hidden inside this glowing spider-shaped cloud are clues about one of astrophysics' biggest questions. How large can stars truly become before physics itself says enough? At the centre of the Tarantula Nebula sits a region so intense that for a long time astronomers were not entirely sure what they were looking at. Early observations revealed an incredibly bright concentration of light buried deep within the nebula's tangled clouds. Through smaller telescopes, the region appeared almost like a single giant object, blazing from the middle of the tarantula's glowing web. That object became known as R136, and initially, some scientists wondered whether it might actually be one impossibly enormous star. That idea sounds slightly ridiculous now, but astronomy has a long tradition of the universe repeatedly doing things humans initially consider ridiculous. Giant black holes, neutron stars, gravitational waves, planets raining molten glass sideways at supersonic speeds. Eventually astronomers learn to become cautious whenever they feel too confident saying, "Surely nature would never do that." As telescope technology improved, researchers realised R136 was not one star after all. It was worse, much worse. R136 turned out to be a densely packed cluster containing some of the most massive and luminous stars ever discovered anywhere in the observable universe. And when astronomers finally resolved the cluster in detail, the numbers became genuinely uncomfortable. Some stars inside R136 appeared to possess masses over 150 times greater than the Sun. Later estimates for a few objects pushed even higher, perhaps above 200 solar masses during their early formation stages. To understand why that startled astronomers so deeply, it helps to appreciate how stars normally behave. Stars survive through balance. Gravity constantly pulls matter inward, trying to crush the star under its own weight. Meanwhile, nuclear fusion inside the core releases enormous energy outward. Radiation pressure pushes against gravitational collapse. As long as those forces remain balanced, the star stays stable. But the larger a star becomes, the more difficult maintaining that balance gets. Massive stars burn fuel at astonishing rates. Their cores become extremely hot and energetic. Radiation pressure rises dramatically. Eventually, astronomers expected stars beyond a certain size to become unstable during formation itself. Outgoing radiation should push surrounding gas away so forcefully that further growth becomes nearly impossible. In simple terms, nature seemed to impose a kind of stellar weight limit. R136 apparently looked at that limit and decided to become a physics problem instead. Inside this cluster, stars formed so massive and luminous that they forced astronomers to reconsider assumptions about how stellar formation works under extreme conditions. And not only are these stars enormous individually, they are packed together extraordinarily tightly. The cluster itself spans only a few light years across, yet contains hundreds of thousands of stars overall, with many giant stars crowded into its central regions. In some places, stellar separations become remarkably small compared to the relative isolation of stars near our Sun. The solar system lives in a fairly quiet neighbourhood. The nearest star system sits over 4 light-years away. If the Sun existed inside R136's dense core, the night sky would appear utterly transformed. Bright stars would dominate the heavens everywhere. Some would outshine our full moon. The darkness humans associate with night might barely exist there at all. And unfortunately for anything hoping to survive peacefully nearby, those stars are not calm. They are monstrous engines of radiation. The brightest stars inside R136 emit millions of times more energy than the Sun. Their surfaces reach temperatures exceeding 40,000 degrees Celsius. Intense ultraviolet radiation floods surrounding space continuously. Stellar winds blast matter outward at speeds reaching thousands of kilometers per second. Even the vocabulary astronomers use begins sounding slightly exhausted around these objects. Hypergiants, Wolf-Rayet stars, supermassive stars, extremely luminous stars. At some point, scientists essentially run out of adjectives and begin quietly staring at spreadsheets, wondering whether the instruments malfunctioned. One particularly famous star inside the cluster, R13601, currently holds the title of the most massive known star ever observed. Estimates suggest it may currently possess roughly 170 solar masses, while initially forming with perhaps over 250 solar masses. That number barely feels real. Our Sun already contains around 330,000 Earth masses. Jupiter, the solar system's giant planet, still contains less than 1,000th the Sun's mass, and R136A1 dwarfs even the Sun enormously. If placed where the Sun sits now, its radiation would sterilize planets far beyond Pluto almost instantly. Fortunately, the universe generally prefers keeping such objects very far away from us. These stars also live frighteningly short lives. A small red dwarf star may survive for trillions of years. The Sun will likely endure around 10 billion years total, but stars inside R136 burn through fuel so aggressively that many may only survive a few million years before collapsing or exploding. They exist like cosmic fireworks, brilliant, violent, brief, and because they're so massive, their deaths will reshape the nebula dramatically. Some may explode as supernovas powerful enough to outshine entire galaxies temporarily. Others might collapse directly into black holes. A few could potentially produce pair instability supernovas, among the most energetic stellar explosions theoretically possible. These are not ordinary stars quietly aging over billions of years. They are unstable giants pouring unimaginable energy into surrounding space every second they remain alive. Interestingly, astronomers still debate how stars this massive form at all. One possibility involves mergers. In crowded environments like R136, forming stars may collide or combine during early development stages. Dense gas clouds and close gravitational interactions could allow multiple massive protostars to merge into even larger objects. Another idea suggests that under extreme conditions, accretion flows onto forming stars become asymmetric. Instead of radiation pushing matter away uniformly, gas might continue falling inward through dense channels or disks, allowing stars to grow larger than expected. Either way, the environment inside R136 appears uniquely suited for producing stellar extremes, and the cluster itself remains remarkably young. Most of its giant stars formed only around 1 or 2 million years ago. In human terms, that sounds ancient. In cosmic terms, it is almost nothing. Dinosaurs lived closer in time to humans than these stars are to typical stellar old age. Actually, many of them will likely explode before Earth's continents significantly rearrange themselves again. Cosmic giants often live shorter lives than mountain ranges. Because the cluster is so young, astronomers essentially observe massive stars near the beginning of their evolution. That makes R136 incredibly valuable scientifically. Researchers can study how these extreme stars behave early in life, before supernova explosions transform them permanently. And the environment surrounding them becomes increasingly chaotic as they evolve. Stellar winds from neighbouring stars collide constantly. Radiation ionizes huge volumes of hydrogen gas. Shock waves race outward. Cavities expand through the nebula. Dense pillars resist erosion temporarily before eventually collapsing or dispersing. The cluster reshapes its surroundings continuously. In some telescope images, enormous bubbles appear carved into nearby gas clouds. Those cavities exist because intense radiation and stellar winds physically push material away from the cluster's core. The stars inside 136 behave almost like giant blowtorches, operating simultaneously in every direction. And yet, paradoxically, these destructive processes may also trigger new star formation elsewhere. Shock fronts compress nearby clouds. Gravity takes over inside denser regions. New protostars emerge. Creation and destruction remain intertwined. One generation of massive stars disrupts the nebula, while simultaneously helping produce future generations. The entire Tarantula Nebula operates almost like a cosmic recycling system, running on nuclear fusion and gravity. Still, conditions near R136 are especially brutal. If humans could somehow observe the cluster safely from nearby, the brightness alone would be overwhelming beyond description. Radiation levels would instantly destroy unprotected biological tissue. Temperatures inside ionized regions remain extraordinarily high. Violent stellar winds continuously hurl matter into surrounding space, and unlike our relatively stable Sun, these stars fluctuate and evolve rapidly. Massive stars lose enormous amounts of mass through stellar winds over time. Some eject material episodically in giant outbursts. Others rotate rapidly enough to distort their shape slightly. They are not neat, simple, glowing spheres. They are turbulent nuclear furnaces barely holding themselves together against their own energy output. One fascinating detail involves luminosity. The Sun converts roughly 600 million tons of hydrogen into helium every second through nuclear fusion. That sounds impressive because it absolutely is impressive. But stars inside R136 exceed that output enormously. Some emit millions of times more energy than the Sun. Their fuel consumption rates become almost absurd. They burn through material so quickly that despite possessing vastly greater mass, their lifespans remain dramatically shorter. It is cosmic financial irresponsibility. The universe gives them gigantic fuel reserves, and they spend everything immediately. Astronomers also study R136 because it may help explain how black holes form under extreme stellar conditions. Massive stars eventually collapse when fusion can no longer support them against gravity. Depending on their final masses and internal structures, the results may include neutron stars or black holes. And recently, gravitational wave observatories like LIGO detected mergers involving surprisingly massive black holes. Some scientists suspect environments like R136 could produce the kinds of giant stellar remnants required for those events. In other words, the cluster may help explain not only stellar formation but also the origins of some black holes now colliding across the universe. That connection feels strangely elegant. Inside one crowded stellar nursery, giant stars form, evolve rapidly, collapse, and potentially create black holes massive enough to generate gravitational waves detectable across billions of light years. All because giant gas clouds collapsed inside a neighbouring galaxy. Astronomy frequently reveals enormous consequences emerging from relatively simple physical rules repeated across vast scales. Gravity gathers matter, fusion ignites, radiation reshapes environments, stars die, new stars form, repeat for billions of years, and occasionally the process creates places like R136, where everything happens at once with extraordinary intensity. The cluster also offers hints about the early universe. Astronomers believe young galaxies shortly after the Big Bang may have formed stars under similarly extreme conditions. Back then, galaxies contained enormous gas reservoirs and experienced rapid star formation episodes far more intense than what typically occurs nearby today. But those ancient galaxies lie incredibly far away. R136 provides something closer, a nearby analogue, a laboratory where scientists can observe extreme stellar populations in remarkable detail without needing to peer across almost the entire observable universe. And the deeper researchers study the cluster, the stranger it becomes. For example, the sheer amount of ultraviolet radiation produced there influences surrounding chemistry dramatically. Molecules get destroyed, hydrogen becomes ionized, dust structures erode, entire regions glow because electrons continuously recombine with stripped atoms after radiation tears them apart again. The nebula shines partly because the stars inside R136 refuse to stop attacking it energetically. Even the colours astronomers capture in telescope images reveal underlying physics. Red regions often trace ionized hydrogen. Blue areas may indicate hotter gas or scattered light. Dark lanes reveal dense dust clouds blocking radiation behind them. The nebula becomes a visible map of energy transfer unfolding across hundreds of light years. And buried at the centre, R136 drives much of the chaos. Yet despite all this violence, stability exists too. Not permanent stability, certainly. Eventually the cluster will evolve dramatically. Giant stars will explode or collapse. Radiation will disperse much of the surrounding gas. The nebula itself will change beyond recognition over millions of years. But for now, gravity still holds the cluster together. Hundreds of thousands of stars orbit collectively through the region. Massive stars dominate energetically, but smaller stars vastly outnumber them overall. Somewhere inside that crowded environment, ordinary stars may quietly form while giant neighbours rage nearby. Perhaps some planetary systems even emerge eventually, though conditions there are harsh enough to make peaceful planetary development rather challenging. Imagine trying to form a stable solar system while nearby stars continuously blast radiation and shock waves through the neighbourhood. It would resemble attempting to build a sandcastle beside an active volcano during a hurricane. Not ideal. Still, the universe occasionally surprises us with resilience, and resilience may actually define the Tarantula Nebula more than violence alone. Because despite overwhelming radiation, catastrophic stellar winds, and future supernovas waiting ahead, star formation continues there relentlessly. The beast feeds itself. One generation creates the conditions for another. Clouds collapse, stars ignite, matter cycles onward. Human beings tend to assume that bigger things are stronger. Bigger buildings, bigger engines, bigger animals. Usually, adding mass creates greater stability and power. A large oak tree survives storms better than a tiny sapling. A blue whale outweighs almost every creature that has ever existed. Even in everyday life, larger machines are often designed to endure heavier workloads. Stars behave differently. In the universe, the largest stars are often the least stable, and inside the Tarantula Nebula, astronomers found some of the most unstable stellar giants ever observed. These are stars living so close to the physical limits of what a star can even be that they spend much of their existence effectively trying to tear themselves apart. That may sound dramatic, but it is actually a fairly accurate summary of their daily routine. The stars inside R136 do not shine peacefully like our Sun. They erupt energy outward with such violence that their own radiation constantly strips material away from their surfaces. They survive only because gravity remains barely strong enough to keep them together against the overwhelming pressure generated inside their cores. Imagine holding a bomb together through sheer weight alone. That is roughly the situation. One of the reasons these stars fascinated astronomers so much is because they seemed almost impossible according to older models of stellar formation. For many years, researchers suspected stars above roughly 100 to 150 solar masses should not exist naturally. The reasoning appeared sensible. As a forming star gathers mass, its core grows hotter and more luminous. Eventually, radiation pressure becomes enormous. Light itself begins pushing outward hard enough to oppose incoming gas. At some point, astronomers expected the star's own radiation to halt further growth completely. And yet the Tarantula Nebula kept producing monsters anyway. R13601 remains the most famous example. Estimates suggest it may currently contain around 170 times the Sun's mass, while its initial formation mass may have exceeded 250 suns. That number becomes even stranger when you consider luminosity. Stars do not scale linearly. A star twice as massive as another does not simply become twice as bright. Luminosity rises dramatically with mass. The most massive stars inside R136 shine millions of times brighter than the Sun. Millions. If the Sun suddenly became as luminous as R13601 while remaining at its current distance from Earth, our planet would not merely heat up. Oceans would vaporize almost instantly. Rocks would melt. The atmosphere itself would become plasma. Humanity's problems would become extremely brief. Fortunately, physics generally keeps such stars very far away from habitable planets, and perhaps wisely so. What makes these giant stars particularly fascinating is how short and chaotic their lives become precisely because they are so massive. Smaller stars are efficient. They conserve fuel carefully and burn slowly over immense spans of time. Massive stars are terrible at long-term planning. They burn through nuclear fuel at absurd rates. Their cores reach staggering temperatures. Fusion reactions proceed furiously. Energy floods outward continuously. The star survives through balance, but the balance becomes increasingly unstable as mass rises. A good comparison might be campfires versus industrial furnaces. A small red dwarf star resembles a carefully controlled candle, capable of burning for trillions of years. A hypermassive star inside the Tarantula Nebula resembles a blast furnace consuming entire train cars of fuel while setting nearby objects on fire accidentally. The star survives only because the process happens in equilibrium temporarily, but temporarily matters enormously. A star like the Sun lives roughly 10 billion years. Some stars inside R136 may survive only 2 or 3 million years before collapsing catastrophically. That means certain stars spend less than 1,000th as long alive despite containing vastly more matter. They are cosmic sprinters, fast, bright, unstable, and doomed almost immediately by stellar standards. One fascinating aspect of these giants involves their internal structure. Inside ordinary stars like the Sun, energy generated in the core moves outward through different transport mechanisms. Some regions transfer energy radiatively, others convectively, like boiling water circulating inside a pot. In giant stars, conditions become much more extreme. Their cores operate at tremendous temperatures and pressures. Fusion proceeds rapidly through multiple stages. Radiation pressure dominates large portions of the star's interior. Turbulence and convection become enormous. These stars are not calm, glowing balls. They are chaotic nuclear environments balanced precariously between collapse and explosion. And because they are so luminous, they continuously lose mass through stellar winds. This process deserves attention because it is genuinely astonishing. The Sun also produces a solar wind. Charged particles stream outward constantly from its outer atmosphere. Earth's magnetic field protects us from most of it, though solar storms occasionally create auroras and interfere with satellites. But the winds from hypermassive stars make the Sun look restrained. Some stars inside the Tarantula Nebula lose matter at rates millions or billions of times greater than the Sun's solar wind. Their radiation pushes enormous amounts of gas into surrounding space continuously. Over time, they may lose substantial fractions of their original mass before even reaching the ends of their lives. In a sense, these stars are evaporating under their own brilliance, and their environments suffer accordingly. Stellar winds collide with nearby gas clouds at incredible speeds, generating shock waves and heating surrounding material dramatically. Radiation ionizes hydrogen across huge regions. Cavities expand through the nebula. Dust structures erode under intense ultraviolet bombardment. The stars become environmental disasters on cosmic scales. Yet astronomers remain deeply grateful for them because giant stars perform crucial roles in the universe. Without massive stars, the cosmos would remain chemically primitive. Hydrogen and helium dominated the early universe after the Big Bang. Heavier elements formed later inside stars through nuclear fusion. Massive stars accelerate this process enormously because their cores reach temperatures high enough to fuse increasingly heavy elements: carbon, oxygen, neon, silicon, iron. Eventually, many of these elements scatter into space through supernovas or stellar winds, enriching future generations of stars and planets. Everything heavier than helium inside your body originated in ancient stars. The calcium in your bones, the oxygen you breathe, the iron in your blood, all forged through stellar nucleosynthesis somewhere in cosmic history, which means stars inside places like the Tarantula Nebula contribute directly to the chemical evolution of galaxies. They are not merely spectacular objects. They are factories producing the ingredients required for planets and biology later. Interestingly, the bigger stars may not form often because nature actively resists creating them. Radiation pressure becomes so intense during formation that giant stars struggle to continue gathering material. Astronomers still debate exactly how the larger stars overcome this barrier. One possibility involves accretion disks. Instead of gas falling inward uniformly, material may flow through flattened rotating disks around forming stars. Radiation escapes more easily along the poles, allowing matter to continue accreting through the disk, despite enormous luminosity. Another possibility involves stellar mergers. In dense environments like R136, protostars or young massive stars may collide and combine, producing even larger objects. The crowded conditions inside the Tarantula Nebula make such interactions more plausible than in quieter stellar neighborhoods. And crowded is definitely the correct word. The central regions of R136 contain extraordinary stellar densities. Massive stars influence one another gravitationally while blasting radiation through shared surroundings. Winds collide. Magnetic fields interact. Shock fronts overlap. It is not a peaceful arrangement. In fact, some stars there may eventually get ejected entirely from the cluster through gravitational interactions. When multiple giant stars orbit closely, complex gravitational encounters can fling objects outward at tremendous speeds. Astronomers call these runaway stars. Imagine being violently expelled from one of the most dangerous stellar environments in the nearby universe by gravitational chaos involving objects millions of times brighter than the Sun. The universe occasionally handles overcrowding issues rather aggressively. Another important detail involves rotation. Many giant stars spin rapidly. Rapid rotation alters their shape slightly, causing equatorial bulging. It also influences internal mixing processes, magnetic fields, and mass loss rates. Some stars rotate so quickly that material near their equators becomes only weakly gravitationally bound. Combined with intense radiation pressure, this creates additional instability. At extreme scales, stars begin approaching something called the Eddington limit. This limit describes the point where outward radiation pressure balances inward gravitational pull. Push beyond it, and the star can no longer retain its outer layers effectively. The biggest stars inside the Tarantula Nebula live dangerously close to this threshold. They survive in a state of near constant tension between gravity and radiation, and eventually gravity loses, but not immediately. Before death arrives, these stars spend millions of years transforming the nebula around them. Ultraviolet radiation floods nearby gas. Stellar winds carve enormous cavities. Heavy elements enrich surrounding clouds. Shock waves compress neighbouring regions. Future generations of stars may eventually form partly from material expelled by earlier giants. The nebula becomes generational. One stellar population influences the next. Astronomers studying the Tarantula Nebula sometimes describe it as resembling starburst galaxies observed in the distant universe. In those galaxies, star formation rates become extremely elevated, producing giant clusters of massive stars rapidly. The Tarantula Nebula provides a nearby example of similar physics unfolding in detail close enough for careful observation. That proximity matters enormously because truly giant stars are rare. The universe overwhelmingly prefers smaller stars. Massive stars consume fuel so quickly and die so young that they remain comparatively uncommon, even in active star-forming regions. To find many giant stars concentrated together requires extraordinary environments, like R136, and even there, they remain temporary. Already some massive stars inside the Tarantula Nebula have exploded as supernovas. Others are approaching instability stages that will eventually end catastrophically. Some may collapse directly into black holes. Others may explode so violently they leave almost nothing behind. A few may generate gamma-ray bursts under certain conditions, releasing staggering amounts of energy through tightly focused relativistic jets. These are among the most powerful events in the universe, and they emerge naturally from the deaths of giant stars barely able to survive their own luminosity. One particularly interesting category involves Wolf-Rayet stars. These evolved massive stars have already lost large portions of their outer hydrogen envelopes through stellar winds. They appear extraordinarily hot and luminous, with powerful outflows shaping surrounding gas. The Tarantula Nebula contains numerous Wolf-Rayet stars, adding further violence to the environment. In telescope images, some produce ring-like nebulae or complex shock structures as their winds collide with earlier expelled material. The stars essentially spend their lives detonating slowly before eventually detonating properly. Even the light from these giants behaves differently than sunlight humans experience daily. Most radiation emitted by hypermassive stars falls heavily into ultraviolet wavelengths invisible to human eyes. Their visible brightness already appears enormous, but much of their energy output occurs beyond ordinary visual perception. The nebula glows partly because surrounding gas absorbs that ultraviolet radiation and re-emits energy at visible wavelengths. In a sense, giant stars illuminate the nebula indirectly by continuously attacking it with radiation. And despite their overwhelming brightness, many remain hidden partially within dense dust and gas clouds. Infrared telescopes like the James Webb Space Telescope help astronomers peer through those obscuring regions to study young massive stars still embedded within stellar nurseries. What Webb revealed shocked researchers repeatedly. Dense knots of protostars, intricate dust structures, previously hidden stellar populations. The deeper humanity looks into the Tarantula Nebula, the more crowded and energetic it becomes, and somewhere inside all that chaos, physics continues testing its own limits. How massive can stars truly become? Can stars exceed 300 solar masses naturally? Do mergers dominate giant star formation? How do stellar winds evolve under such extreme luminosities? The Tarantula Nebula became one of astronomy's greatest laboratories precisely because it contains objects living near the edge of what stars can physically endure. These giants exist in unstable balance barely, surviving the pressure generated by their own light. A star does not need to explode to become dangerous. That is one of the first things astronomers learned while studying places like the Tarantula Nebula. Popular imagination usually treats stars as relatively stable objects right up until the dramatic moment they become supernovas, quietly shining for millions or billions of years, then suddenly detonating in spectacular fashion like cosmic fireworks finally reaching their finale. Massive stars are far less patient than that. Long before they die, they begin violently reshaping everything around them. Inside the Tarantula Nebula, this process happens continuously. Giant stars flood surrounding space with ultraviolet radiation, unleash stellar winds moving at millions of kilometers per hour, and carve enormous cavities through clouds that once formed them. The result is chaos on scales difficult to picture clearly. Gas clouds collapse while neighbouring regions get blasted apart. Shock fronts collide with dust pillars. Entire structures evaporate under radiation. Dense clumps survive temporarily like islands inside a storm before eventually eroding away too. And through all of it, the nebula keeps evolving. It helps to start with radiation because massive stars produce absurd amounts of it. The Sun already emits staggering energy. Every second it converts roughly 600 million tons of hydrogen into helium through nuclear fusion. That process releases enough energy to sustain all life on Earth while still leaving enormous excess power streaming into space. But giant stars inside the Tarantula Nebula exceed the Sun enormously. Some emit millions of times more luminosity. Their surfaces burn at temperatures exceeding 40,000 degrees Celsius, far hotter than the Sun's roughly 5,500 degree surface. At those temperatures, stars radiate huge amounts of ultraviolet light, energetic enough to ionize surrounding hydrogen gas. Ionization simply means electrons get stripped away from atoms. Under ordinary conditions, hydrogen atoms contain one proton and one electron. Ultraviolet radiation from giant stars carries enough energy to knock electrons loose, leaving ionized plasma behind, and that plasma glows. Much of the Tarantula Nebula's famous appearance comes from ionized hydrogen, radiating visible light after electrons recombine with atoms repeatedly. The nebula shines because giant stars continuously bombard it with radiation energetic enough to alter atomic structure across enormous distances. The process resembles cosmic sunburn on a galactic scale, except instead of damaging skin cells, the radiation transforms entire clouds hundreds of light years wide, and radiation is only part of the problem. Massive stars also generate stellar winds far stronger than anything produced by the Sun. Solar wind from our own star already affects Earth significantly, It shapes planetary magnetospheres, creates auroras near the poles, and occasionally disrupts satellites or electrical systems during intense solar storms. But compared to giant stars inside the Tarantula Nebula, the Sun behaves almost politely. The stellar winds from hypermassive stars are relentless torrents of charged particles blasted outward continuously at incredible speeds. Some winds travel several thousand kilometers per second. Matter streams into surrounding space with such force that it physically sculpts the nebula around the stars. Imagine aiming dozens of gigantic industrial pressure washers at a cloud continuously for millions of years. Eventually cavities form. That is exactly what happens inside the Tarantula Nebula. Telescope images reveal enormous bubbles and hollowed regions carved into surrounding gas. These structures are not empty by accident. Stellar winds and radiation physically pushed material away over time, excavating giant cavities through the nebula. And because many massive stars exist close together inside clusters like R136, their winds collide constantly. Those collisions create shock fronts. When supersonic winds slam into surrounding gas or other winds, temperatures rise dramatically. Matter compresses. Turbulence spreads. X-rays emerge from extremely hot shocked material. The nebula becomes less like a quiet cloud and more like an active weather system powered by nuclear fusion instead of sunlight. Actually, weather systems might be too, gentler comparison. Hurricanes eventually lose energy. The Tarantula Nebula keeps receiving fresh input from giant stars continuously. One particularly fascinating effect involves photoevaporation. Dense gas clouds inside the nebula often resist erosion temporarily because gravity helps hold them together. But ultraviolet radiation gradually heats outer layers, causing material to stream away into surrounding space. Over time, dense structures shrink and dissolve. Some telescope images show towering pillars or finger-like formations pointing toward bright star clusters. These structures exist because denser regions survive erosion longer than softer surrounding gas. The famous pillars of creation inside the Eagle Nebula work similarly, though conditions in the Tarantula Nebula are often even more extreme. Radiation essentially sandblasts the nebula, and while that sounds destructive, it also influences future star formation in complicated ways. For many years, astronomers debated whether massive stars primarily suppress or trigger star formation nearby. The answer appears to be both. Radiation and winds certainly destroy some clouds, dispersing gas before gravity can collapse it into stars. But shock fronts from expanding bubbles may also compress neighbouring regions tightly enough to trigger collapse elsewhere. It becomes a cosmic balancing act. One area gets sterilized while another becomes fertile. One cloud evaporates while another condenses. Destruction and creation remain tangled together continuously. That complexity makes the Tarantula Nebula extraordinarily valuable scientifically because it reveals star formation not as a neat isolated process but as a dynamic ecosystem of interacting forces. And the interactions become intense. Some cavities inside the nebula span dozens or even hundreds of light years. The energy required to excavate such enormous structures is staggering. Giant stars pour mechanical energy into their surroundings through winds constantly over millions of years. The cumulative effect becomes enormous. In some regions, astronomers observe superbubbles, gigantic expanding cavities, formed through combined winds and supernova explosions from multiple massive stars. These structures may eventually rupture surrounding gas layers, venting hot material outward into larger galactic environments. In other words, giant stars inside the Tarantula Nebula do not merely affect nearby clouds, they influence the structure of entire regions within the Large Magellanic Cloud itself. The scale becomes difficult to overstate. Even individual stars inside R136 emit more energy than humanity could meaningfully conceptualize in everyday terms. Combined together inside dense clusters, they create feedback systems powerful enough to reshape enormous portions of a neighbouring galaxy. And still the stars keep forming. That persistence fascinates astronomers because the environment should almost seem too hostile for continued star formation. Imagine trying to grow delicate seedlings beside active volcanoes, while hurricane winds constantly rip through the landscape. That would still undersell the situation somewhat. Yet inside dense molecular clouds shielded partially by dust and gas, gravity continues winning often enough to create new stars. Infrared observations reveal hidden protostars buried deep within obscured regions of the nebula. Some remain wrapped inside thick cocoons of dust invisible in ordinary visible light. Others already begin clearing surrounding material through jets and outflows. The nebula contains multiple generations of stellar evolution simultaneously. Newborn protostars, young massive stars, evolved giants, supernova remnants, everything overlapping together. One especially dramatic consequence of giant star radiation involves chemistry. Ultraviolet light alters molecules throughout surrounding clouds. Delicate compounds break apart under energetic bombardment. Dust grains heat up. Ionization changes how gas behaves magnetically and thermodynamically. The environment around massive stars becomes chemically harsh, and that matters for planets too. Astronomers suspect planetary systems forming near giant stars may struggle under such conditions. Radiation can erode protoplanetary disks, the rotating structures of gas and dust surrounding young stars where planets eventually form. Inside quieter regions of the Milky Way, disks may survive millions of years peacefully enough to assemble planets gradually. Inside the Tarantula Nebula, nearby giant stars behave like cosmic leaf blowers aimed directly at the construction site. Some disks probably get stripped apart before planet formation finishes. Others may survive partially. The exact outcomes remain an active area of research. Still, the environment there clearly favours violence over tranquility. Another fascinating feature involves the colour and structure visible in telescope imagery. People sometimes assume astronomical photographs are artificially dramatic. In reality, many structures truly are extraordinarily intricate. Filaments twist through space, shock fronts curve around cavities, dark dust lanes snake across glowing hydrogen clouds. Physics creates beauty almost accidentally. Hydrodynamics, gravity, magnetism, and radiation interacting across enormous scales generate shapes that appear strangely organic, despite emerging from entirely non-living processes. The Tarantula Nebula especially resembles something biological in many images, which likely contributed to its spider-inspired name. Long glowing filaments stretch outward like legs. Bright clusters resemble eyes or central body structures. Dust clouds twist into tangled patterns across illuminated gas. Of course, humans excel at seeing familiar patterns everywhere. Give people random clouds on Earth and someone will spot a rabbit. Give humanity a nebula spanning hundreds of light years and eventually someone says, "That one looks concerningly spider-shaped." Still, beneath the visual beauty lies astonishing violence. Temperatures inside ionized regions may reach around 10,000 degrees Celsius. Shock-heated gas from wind collisions becomes far hotter still, reaching millions of degrees in some cases. If space contained air dense enough to carry sound, the Tarantula Nebula would probably be deafening. Fortunately for astronauts everywhere, space remains mostly vacuum. That silence creates an interesting contrast. Astronomical images often appear calm and still. Yet the environments they depict may contain turbulent gas flows, expanding shock fronts, violent radiation fields, and explosive stellar activity unfolding continuously. The universe only appears peaceful because humans observe it across very short timescales. If the Tarantula Nebula could be viewed in accelerated time, spanning millions of years compressed into minutes, it would likely resemble boiling weather systems mixed with explosions. Clouds would ripple outward, cavities would expand, stars would ignite and vanish. Shock waves would race through glowing gas. Structures would form and dissolve constantly. Even the stars themselves would evolve noticeably over such timescales. Massive stars lose matter so rapidly that they visibly alter surrounding environments during relatively brief cosmic intervals. Some eject shells of gas episodically, others produce asymmetric winds shaped partly by rotation and magnetic fields, and eventually the violence escalates further. Because stellar winds and radiation are merely preparation for what comes next, massive stars inside the Tarantula Nebula are effectively loading the environment with energy long before their final explosions occur. When supernovas eventually erupt, they expand into regions already shaped by millions of years of stellar feedback. Existing cavities channel blast waves, dense clouds redirect shocks, heavy elements scatter into environments already chemically enriched by stellar winds. The nebula evolves through cumulative layers of disturbance. One generation of stars modifies conditions for the next generation, and sometimes the effects become surprisingly large-scale. Astronomers studying giant star clusters discovered that collective stellar feedback may regulate star formation across entire galaxies. Too much star formation creates too many massive stars. Those stars then generate winds, radiation, and supernovas capable of dispersing gas and suppressing further collapse temporarily. Galaxies may partially self-regulate through stellar violence. The Tarantula Nebula provides a nearby example of this process operating intensely enough for detailed observation, and detailed observation became dramatically easier. With modern telescopes, the Hubble Space Telescope revealed stunning visible light structures across the nebula. Then the James Webb Space Telescope expanded that view enormously by observing infrared wavelengths capable of penetrating dust clouds previously obscuring hidden regions. Suddenly astronomers could peer deeper into stellar nurseries embedded within the nebula itself. Newly forming stars appeared. Complex dust structures emerged. Previously invisible feedback interactions became clearer. And one thing became increasingly obvious. The Tarantula Nebula is not remotely stable in the long term. It is transitional, temporary. A giant turbulent phase in the ongoing evolution of matter inside the Large Magellanic Cloud. Eventually enough massive stars will explode or disperse surrounding gas that the nebula's current appearance will vanish completely. The giant glowing structures humans admire today exist only briefly compared to galactic timescales. Millions of years from now, the region may look entirely different, perhaps quieter, perhaps dominated by supernova remnants and black holes, perhaps populated by older star clusters drifting gradually apart. The spider-shaped glow itself will not survive forever. That impermanence feels oddly important somehow. Humans often imagine cosmic objects as eternal because their lifespans dwarf ours so completely. But even giant nebulae are temporary structures. Stars form, alter their surroundings, explode, and move on. For most of their lives, massive stars fight a constant battle against gravity. Fusion inside their cores releases enormous energy outward. Gravity pulls inward relentlessly. As long as those forces remain balanced, the star survives. Hot, unstable, and violent perhaps, but still alive. Eventually the balance fails, and when giant stars inside places like the Tarantula Nebula die, they do not fade quietly into darkness. They explode with such force that for a brief time, one dying star can outshine entire galaxies containing hundreds of billions of other stars combined. That is what makes supernovas so astonishing. Not merely their brightness, their scale. Human beings evolved around explosions small enough to fit comfortably inside weather systems or battlefields. Even the largest volcanic eruptions in Earth's history become tiny compared to the energy released when a massive star collapses and detonates. A supernova does not simply destroy a star. It transforms entire regions of space around it. And inside the Tarantula Nebula, those explosions are not rare historical accidents from distant cosmic history. They are part of the environment itself. Some stars there already exploded long ago. Others are approaching collapse right now, though thankfully right now in astronomy often still allows several 100,000 years for preparation. Still, the nebula is full of future catastrophes waiting patiently. To understand why supernovas happen, we need to revisit stellar fusion for a moment. Stars survive by fusing lighter elements into heavier ones inside their cores. Hydrogen becomes helium. Helium eventually fuses into carbon and oxygen in larger stars. Massive stars continue farther, producing neon, silicon, sulfur, and eventually iron. And iron creates a problem. Fusion normally releases energy, because lighter atomic nuclei combine into more stable, heavier nuclei. But iron sits near the peak of nuclear binding energy. Fusing iron does not release energy efficiently anymore. It consumes energy instead. That means once a massive star develops an iron core large enough, fusion can no longer support the star against gravity. The core suddenly loses its ability to generate sufficient outward pressure, and gravity immediately takes advantage. The collapse happens astonishingly fast. The star's core implodes inward in seconds, reaching densities so extreme that atomic structure itself begins breaking down. Electrons and protons combine into neutrons. Matter compresses violently. Temperatures rise into the billions of degrees. Then the collapse rebounds catastrophically. The outer layers crash inward and slam against the suddenly incompressible, neutron-rich core. A shock wave erupts outward through the star. Neutrinos flood into surrounding material. Enormous energy gets released almost simultaneously, and the star explodes. Not metaphorically, actually explodes. The blast wave tears through the outer layers at tremendous speeds, ejecting stellar material across space. Heavy elements forged inside the star scatter into the surrounding nebula. Radiation surges outward. Nearby gas clouds get compressed, heated, and reshaped. For a short time, the dying star becomes one of the brightest objects in its galaxy. Inside the Tarantula Nebula, such explosions have likely occurred repeatedly across millions of years. Astronomers can actually see evidence of past supernovas there. Expanding shock fronts, supernova remnants, and chemically enriched regions reveal places where giant stars already reach the ends of their short, violent lives. One particularly famous remnant nearby within the Large Magellanic Cloud is SN 1987A. This supernova became one of the most important astronomical events of the modern era, because it occurred relatively close to Earth in cosmic terms, only about 168,000 light-years away. When the light reached Earth in 1987, astronomers suddenly had the chance to study a nearby supernova in extraordinary detail using modern instruments, and it changed astrophysics significantly. The progenitor star, Sanduleak -69°202, was a blue supergiant, which surprised researchers because prevailing theories at the time expected many core collapse supernovas to originate primarily from red supergiants. The universe once again reminded scientists not to become too confident. SN 1987. A also allowed astronomers to detect neutrinos directly from a supernova for the first time. Neutrinos are tiny, nearly massless particles produced in enormous quantities during core collapse. Trillions pass through your body every second normally without interacting with anything. During a supernova, the numbers become absurd. The collapsing core releases so many neutrinos that for a brief moment they carry away most of the explosion's energy. Detectors on Earth captured a small burst from SN 1987A, confirming important aspects of supernova theory, all because one giant star died inside the Large Magellanic Cloud. And the Tarantula Nebula likely hosts many future versions of such events waiting ahead. The stars inside R136 are especially concerning from a stability perspective. Many possess enough mass to end their lives dramatically. Some may leave behind neutron stars, objects so dense that a teaspoon of neutron star material would weigh billions of tons on Earth. others may collapse into black holes, and some of the largest might experience even stranger fates. One possibility involves pair instability supernovas. This type of explosion occurs only in extremely massive stars under particular conditions. At extraordinarily high temperatures, gamma rays inside the core can transform into electron-positron pairs, reducing radiation pressure suddenly. The core destabilizes rapidly, triggering runaway collapse and explosive oxygen fusion. The resulting explosion may become so powerful that the entire star gets obliterated completely. No neutron star, no black hole, nothing left behind except expanding debris. The star effectively unbuilds itself. Astronomers suspect pair instability supernovas were more common in the early universe, when giant stars formed more frequently. The Tarantula Nebula's extreme stellar population makes it one of the best nearby environments where such events might potentially occur, which means some stars there may eventually produce explosions among the most energetic events possible for ordinary stars. And even ordinary feels like the wrong word here. The effects of supernovas extend far beyond dramatic flashes of light. These explosions drive chemical evolution across galaxies. Many heavy elements essential for rocky planets and biology form or scatter during supernova events. Gold, uranium, iodine, calcium, iron and countless other elements owe part of their cosmic journey to exploding stars. Your body contains atoms forged in ancient stellar catastrophes. The iron in your blood likely passed through supernova explosions billions of years before Earth existed. The calcium in your bones emerged from dying stars. Human beings are built partly from recycled stellar debris, which sounds poetic until you remember the recycling process involved stars detonating with unimaginable violence across space. Inside the Tarantula Nebula, supernovas also influence future star formation directly. Shockwaves expand outward through surrounding gas clouds, compressing some regions while dispersing others. Dense clumps may collapse under increased pressure, triggering new protostars. Nearby structures may erode or fragment. The nebula responds dynamically to each explosion. Imagine throwing enormous stones repeatedly into a shallow pond already boiling violently. Waves collide with existing turbulence. Patterns shift continuously. Nothing remains isolated from anything else. That is roughly the situation inside giant star-forming regions. And because the Tarantula Nebula contains so many massive stars crowded together, the explosions may sometimes overlap in complicated ways. One supernova erupts into an environment already shaped by stellar winds from neighbouring giants. Previous explosions carved cavities nearby. Radiation fields altered gas temperatures already. Magnetic fields twisted through the region. The blast wave enters chaos immediately. Astronomers studying supernova remnants often observe intricate structures shaped partly by these pre-existing environmental conditions. Expanding shells become asymmetric. Shock fronts interact with dense clouds differently depending on local conditions. Supernovas are not neat spherical fireworks in practice. They are messy, complicated, violent hydrodynamic events unfolding through already turbulent environments, and their aftermaths can persist for hundreds of thousands of years. Supernova remnants continue expanding long after the initial explosion fades. Hot-shocked gas emits X-rays. Magnetic fields accelerate charged particles. Filaments twist through surrounding space. Heavy elements spread outward gradually into the interstellar medium. Eventually, the debris may mix into future generations of stars and planets. One generation dies, so another may form later. Astronomy frequently operates through cycles like this, and perhaps nowhere nearby are those cycles more intense than inside the Tarantula Nebula. Another fascinating aspect involves black hole formation. Some massive stars may collapse directly into black holes with relatively weak explosions or none at all. Instead of detonating spectacularly, the core implodes beyond recovery, forming an object whose gravity becomes so strong that not even light escapes. The outer layers may still get expelled partially, but the central object disappears from ordinary observation entirely. The Tarantula Nebula likely contains black holes already formed from earlier generations of massive stars. Astronomers suspect some may exist inside binary systems, where black holes interact gravitationally with companion stars. Matter falling toward black holes can emit intense X-rays, revealing otherwise invisible objects indirectly. And remarkably, environments like the Tarantula Nebula may help explain gravitational wave events detected recently by observatories such as LIGO and Virgo. These detectors discovered mergers involving unexpectedly massive black holes. One explanation suggests giant stars forming in dense clusters, like R136, may eventually collapse into large black holes that later merge through gravitational interactions. In other words, violent stellar nurseries may produce black hole systems capable of shaking space-time itself billions of years later. The consequences ripple forward across cosmic history. One generation of giant stars creates heavy elements, black holes, shock waves, and altered galactic environments influencing everything afterward, and the Tarantula Nebula remains full of stars destined to continue that process. Some are already unstable. Massive stars often evolve unpredictably near the ends of their lives. They may shed outer layers episodically, brighten dramatically, or undergo violent eruptions before final collapse. Eta Cachenet inside our own galaxy provides a famous example of a giant unstable star that experienced enormous outbursts in the 19th century without fully exploding yet. The Tarantula Nebula likely contains numerous similar stellar time bombs hidden among its crowded populations. Astronomers monitor such stars carefully, because predicting exactly when giant stars explode remains surprisingly difficult. A star may appear relatively stable right up until final collapse begins. The core changes happen deep inside, hidden beneath thick outer layers. From far away, the star may continue shining normally, while catastrophic instability develops invisibly within. Then suddenly the explosion begins, and for a brief period the dying star radiates extraordinary brilliance across space. If a supernova occurred close enough to Earth, it could appear visible during daytime. Historical records describe supernovas bright enough to cast shadows at night. Fortunately, the Tarantula Nebula sits far enough away that even its future explosions pose no threat to Earth itself. We may simply observe them as spectacular astronomical events eventually when their light arrives. Though eventually matters here too. Remember, the nebula lies roughly 160,000 light-years away. Any supernova we observe there already happened long ago. Some stars inside the Tarantula Nebula may have exploded, while early humans still hunted with stone tools. Their light simply has not reached us yet. The universe keeps unfolding beyond our awareness continuously. Right now, somewhere in that neighbouring galaxy, giant stars are likely dying violently. Shock waves are expanding, heavy elements are scattering, black holes may be forming, and Earth continues drifting quietly around an ordinary star, temporarily sheltered from most of that chaos by distance alone. Distance, in astronomy, often equals survival. Still, even from far away, supernovas in the Tarantula Nebula matter enormously, because every explosion helps shape the next stage of the nebula's evolution. Gas clouds compress, chemistry changes, new stars eventually emerge from material enriched by earlier generations. The cycle continues. When people first see detailed images of the Tarantula Nebula, they often ask the same question: is that what it really looks like? It is a fair question because the colours appear almost unreal. Brilliant reds spread across enormous clouds. Blue filaments twist through glowing gas. Dark pillars cut across bright regions like shadows suspended in space. Gold, purple, pink, and orange structures overlap in tangled patterns stretching hundreds of light-years wide. The images resemble paintings more than astronomy. And yet the strange thing is that the underlying physics creating those colours is completely real. The Tarantula Nebula truly is glowing. not because it is burning like fire, but because radiation from giant stars continuously energizes enormous clouds of gas spread throughout the region. To understand why the nebula appears so colourful, we need to start with something deceptively simple. Atoms are picky. They only absorb and emit specific amounts of energy. Electrons occupy defined energy levels around atomic nuclei, and when electrons move between those levels, they release or absorb photons at particular wavelengths. That process creates spectral lines, and spectral lines allow gas clouds across space to glow with characteristic colours depending on what elements they contain and how those elements become energized. Inside the Tarantula Nebula, hydrogen dominates. Hydrogen remains the most abundant element in the universe by far. Giant clouds of it drift throughout galaxies, waiting for gravity, radiation, and time to shape them into future stars. But hydrogen does not naturally glow bright red all by itself. It requires energy, and the Tarantula Nebula contains plenty of that. Massive stars inside regions like R136 emit enormous quantities of ultraviolet radiation. This radiation carries enough energy to ionize hydrogen atoms by knocking electrons loose entirely. The result becomes ionized hydrogen plasma. Eventually, free electrons recombine with hydrogen nuclei. As the electrons settle back into lower energy states, they release photons at specific wavelengths. One especially important wavelength, called hydrogen alpha, appears deep red. That red glow dominates many nebula images, so when you look at the Tarantula Nebula's glowing crimson clouds, you're essentially seeing enormous volumes of hydrogen continuously excited by radiation from giant stars. The nebula shines because nearby stars keep attacking it energetically, and the scale involved is absurd. These glowing structures stretch across hundreds of light years. Entire clouds become ionized over enormous distances because giant stars pour ultraviolet light outward continuously. A single massive star can influence surrounding gas across regions vastly larger than the solar system. Thousands of such stars together create something extraordinary. The Tarantula Nebula becomes almost like a cosmic fluorescent sign powered by nuclear fusion. Of course, hydrogen is not the only element present. Astronomers observe oxygen, sulfur, helium, nitrogen, carbon, and many other elements throughout the nebula. Each produces characteristic spectral emissions under different conditions. Oxygen, for example, often appears blue-green in certain telescope images because doubly ionized oxygen emits strongly at specific visible wavelengths. Sulfur emissions may appear reddish-orange. Different filters isolate different gases. This is why astronomical photographs sometimes look more colourful than human vision alone might perceive directly through a telescope. Cameras and detectors collect light over long exposures and isolate specific wavelengths carefully. Scientists then assign visible colours to different emissions to reveal physical structures and chemical compositions clearly. Contrary to popular belief, this is not fake, it is translation. Human eyes evolved for survival on Earth, not for interpreting faint interstellar plasma clouds. Astronomical imaging simply converts otherwise invisible information into forms humans can examine meaningfully. And the information hidden inside those colours is astonishing. Different wavelengths reveal temperature, density, chemical composition, ionization state, shock fronts, and radiation intensity across the nebula. In some regions, hot ionized gas dominates. Elsewhere, colder dust clouds absorb light and appear dark. Shock-heated material glows differently than calmer regions. The nebula becomes a giant visible map of physics unfolding across space. One particularly striking feature involves dust. Dust sounds unimpressive at first. On Earth, dust mostly inspires cleaning products and mild frustration. In space, however, dust plays a crucial role in cosmic evolution. Interstellar dust consists of tiny solid particles made from heavier elements like carbon, silicon, oxygen and metals forged in earlier generations of stars. These grains drift throughout galaxies mixed with gas clouds, and inside the Tarantula Nebula, dust creates some of the most dramatic visual structures. Dark lanes and towering pillars appear because dense dust clouds block visible light behind them. Unlike glowing hydrogen gas, dust does not usually emit bright visible light directly. Instead, it absorbs and scatters radiation. That is why some regions look shadowed. The famous dark tendrils crossing bright glowing clouds are not empty space. They are often dense concentrations of dust obscuring brighter material behind them, and those dusty regions matter enormously because stars form inside them. Dust helps cool collapsing gas clouds by radiating away heat. Without cooling, gas resists gravitational collapse more strongly. Dust grains also provide surfaces where molecules can form, including molecular hydrogen, an important ingredient in star formation. So the dark regions inside the Tarantula Nebula are not lifeless voids, they are stellar nurseries hidden behind curtains of dust. Infrared telescopes reveal this beautifully. Visible light struggles to penetrate dense, dusty clouds because dust absorbs and scatters shorter wavelengths effectively. Infrared light, however, passes through more easily. That is one reason the James Webb Space Telescope transformed our understanding of regions like the Tarantula Nebula so dramatically. Webb peers through dust. Suddenly, structures once hidden become visible. Young stars emerge from obscured cocoons. Dense knots of forming material appear inside dark regions previously thought almost opaque. The nebula changes character entirely depending on wavelength. In visible light, it appears tangled and dramatic. In infrared, hidden stellar populations emerge. In X-rays, hot-shocked gas from stellar winds and supernovas dominates. In radio wavelengths, cold hydrogen clouds become visible. Every telescope reveals a different layer of reality, and together they show that the Tarantula Nebula is far more complex than ordinary images alone suggest. One fascinating detail involves reflection versus emission nebulae. Some nebulae shine because gas emits light directly after ionization, like much of the Tarantula Nebula. Others shine primarily because dust reflects nearby starlight. Reflection nebulae often appear blue because dust scatters shorter wavelengths more efficiently, similar to why Earth's sky appears blue. The Tarantula Nebula contains elements of both processes in different regions, but the dominant visual impression comes from emission, enormous glowing hydrogen clouds energized by giant stars, and those stars are relentless. Ultraviolet radiation continuously alters surrounding gas. Stellar winds carve cavities. Shock fronts heat material. Dust structures erode under radiation exposure. The nebula changes shape over time because energy keeps flowing through it. Nothing there remains static. Even the colors themselves reflect ongoing physical processes. Brighter red regions often indicate intense ionization. Blue or greenish structures may trace hotter, oxygen-rich areas. Dark silhouettes reveal dense dust concentrations resisting erosion temporarily. Some structures resemble pillars because denser material survives radiation longer than surrounding gas. Eventually, even those pillars erode too. The nebula behaves like a giant cosmic sculpture, carved continuously by light and wind. And because the Tarantula Nebula contains such extreme stars, the sculpting becomes violent. In calmer regions of space, gas clouds evolve more gently. Here, giant stars blast surrounding material aggressively enough to reshape structures across hundreds of light years. Astronomers studying the nebula sometimes describe feedback mechanisms operating there. Radiation and winds from massive stars influence nearby gas clouds, which in turn affects future star formation. The colors reveal those feedback processes visually. Bright ionized fronts mark places where radiation collides with denser material. Expanding bubbles show where stellar winds pushed gas outward. Shock-heated regions glow differently than colder clouds nearby. Physics paints the nebula continuously, and occasionally the results become strangely beautiful despite the underlying violence involved. Human beings often react emotionally to nebula imagery because the structures appear familiar somehow. Clouds, smoke, rivers, roots, waves, storms. The brain searches for recognizable patterns automatically. The Tarantula Nebula especially feels organic in many photographs. Its filaments resemble tangled threads. Cavities appear almost lung-like or webbed. Dust pillars rise like dark cliffs against glowing skies. But beneath that apparent artistry lies brutal astrophysics. Temperatures inside ionized regions may exceed 10,000 degrees Celsius. Radiation levels near giant stars become lethal instantly. Shock waves from stellar winds and supernovas race outward continuously. Beauty in astronomy frequently emerges from violent processes. Supernovas create elegant, expanding remnants while destroying stars completely. Black holes produce luminous accretion disks through catastrophic gravity. Galaxies collide and generate brilliant starbursts. The Tarantula Nebula follows the same pattern. Its extraordinary appearance comes directly from extreme stellar violence shaping matter across enormous scales. Another interesting aspect involves time. The colours humans observe today represent conditions from roughly 160,000 years ago because light from the nebula required that long to reach Earth. Some structures visible now may already look different in the present-day nebula. Massive stars evolve rapidly. Shock fronts expand. Dust pillars erode. Supernovas erupt. The Tarantula Nebula changes continuously, while humanity watches delayed images from far away. Astronomy always involves looking backward in time, and because giant stars inside the nebula live such short lives, the region evolves relatively quickly in cosmic terms. Millions of years from now, the glowing structures visible today may vanish entirely. The nebula itself is temporary. Eventually enough stellar winds and supernovas will disperse surrounding gas. Star formation rates may decline. Dust clouds may dissipate or collapse into future stars. The spider-shaped appearance humans admire now exists only briefly on galactic timescales. That impermanence feels strangely important somehow. The universe does not preserve beautiful things forever. Nebulae form, evolve, and disappear. Stars ignite and die. Galaxies change shape slowly over billions of years. Even giant glowing structures hundreds of light years wide remain temporary moments inside longer cosmic stories. Still, while the Tarantula Nebula exists in its current form, it provides astronomers with one of the most valuable natural laboratories in the nearby universe, because its colours reveal not only beauty but history. The distribution of gas shows where radiation dominates. Dust structures reveal regions resisting erosion. Heavy elements trace previous generations of stellar explosions. Shock fronts expose ongoing feedback processes. The nebula becomes readable, almost like weather maps for a cosmic storm. And perhaps most importantly, the conditions there resemble environments believed common in the early universe. Young galaxies billions of years ago likely contained similarly intense star-forming regions packed with massive stars. But those galaxies lie incredibly far away and appear faint even through powerful telescopes. The Tarantula Nebula provides something closer, a nearby analogue, a visible example of what ancient stellar nurseries may have looked like when galaxies were young and chaotic. In a sense, its strange colours illuminate cosmic history itself. One of the strangest things about the Tarantula Nebula is that astronomers do not study it only to understand a nearby cloud. They study it because it may resemble places that existed billions of years ago near the beginning of cosmic history. That sounds slightly absurd at first. How can one nebula inside a neighbouring galaxy help explain the ancient universe itself? The answer involves scale, chemistry, and the strange way astronomy turns distance into time travel. When humans look deeper into space, they also look farther into the past. Light takes time to travel, and the universe is unimaginably large. The farther away an object sits, the longer its light has been travelling before reaching Earth. This means telescopes observing distant galaxies are actually seeing ancient versions of those galaxies. Some appear as they existed billions of years ago, not long after the Big Bang itself. And those early galaxies looked very different from many galaxies nearby today. They were smaller, messier, richer in gas, and far more violent in their star formation. Instead of calmly producing stars over long periods, many young galaxies experienced enormous bursts of activity. Giant clouds collapsed rapidly. Massive stars formed in huge numbers. Radiation flooded surrounding space. Supernovas erupted constantly. The early universe was busy, very busy. Galaxies had not yet settled into the relatively organized spiral structures people often imagine when thinking about systems like the Milky Way. Instead, many were chaotic collections of turbulent gas and rapidly forming stars. And oddly enough, the Tarantula Nebula resembles those conditions more closely than most nearby regions do. That realization transformed the nebula from an interesting local object into one of the most important laboratories in modern astrophysics. Because while ancient galaxies remain incredibly distant and difficult to observe in detail, the Tarantula Nebula sits close enough for humanity to examine carefully. It acts almost like a preserved sample of earlier cosmic behavior operating in our galactic neighborhood. To understand why, we need to talk about metallicity again. Astronomers use the word metals in a wonderfully confusing way. In astrophysics, everything heavier than hydrogen and helium counts as a metal. Oxygen, metal, carbon, metal, neon, also metal. If a chemist hears this conversation, they usually become slightly distressed. But the distinction matters enormously in astronomy, because the early universe contained very few heavy elements. Right after the Big Bang, the cosmos consisted mostly of hydrogen and helium with tiny traces of lithium. Heavier elements did not exist yet because stars had not produced them. Only later, through nuclear fusion and supernova explosions, did galaxies gradually become enriched with heavier atoms. This means ancient galaxies possessed much lower metallicity than galaxies like the modern Milky Way, and the large Magellanic Cloud where the Tarantula Nebula lives also has relatively low metallicity compared to our galaxy. That similarity matters. Lower metallicity changes how gas behaves during star formation. Heavy elements help cool gas clouds efficiently by radiating energy away. Dust formation also depends heavily on heavier elements. When metallicity stays low, clouds collapse differently. Massive stars may form more easily. Radiation interacts with surrounding environments differently. Stellar winds behave differently too because heavy elements contribute strongly to how radiation drives outflows from giant stars. In simple terms, stars born in low metallicity environments may grow larger and behave more violently. The Tarantula Nebula demonstrates exactly that. It contains some of the most massive stars ever discovered, including giants inside R136 exceeding 150 or even 200 solar masses. Such stars may have been more common in the early universe when metallicity remained low across many galaxies. So by studying the Tarantula Nebula, astronomers may be observing conditions partly similar to those that shaped the first generations of massive stars billions of years ago. And those first stars changed everything. Before stars existed, the universe remained relatively simple. Hydrogen and helium drifted through expanding space. No planets existed. No oxygen-filled atmospheres. No rocky worlds circled stars because there were no stars yet. Then gravity began gathering gas into the first stellar nurseries. Those early stars were probably enormous. Without many heavy elements cooling the gas efficiently, collapsing clouds may have formed giant stars preferentially. Some theoretical models suggest the very first stars, called population 3 stars, may have grown hundreds of times more massive than the Sun. If true, they would have lived short, violent lives. Massive stars burn fuel quickly, they emit enormous ultraviolet radiation, they explode spectacularly, and through those explosions they manufacture and scatter heavier elements into surrounding space. In a very real sense, giant stars transform the young universe from chemically simple into chemically rich. Everything required for planets and biology came later from their nuclear furnaces. The Tarantula Nebula may therefore offer clues about how that transformation unfolded. Not perfectly, of course. The modern universe differs significantly from conditions shortly after the Big Bang. The Tarantula Nebula already contains many heavy elements compared to truly primordial environments. Still, it provides one of the closest nearby analogues to ancient starburst regions astronomers can observe directly. And the similarities are striking. The nebula forms stars at extraordinary rates. It contains dense clusters packed with giant stars. Radiation floods surrounding space intensely. Supernovas reshape the environment continuously. These are precisely the kinds of conditions astronomers infer from observations of distant young galaxies. The difference is proximity. Ancient galaxies lie billions of light years away. Even the James Webb Space Telescope sees them only as faint, tiny smudges because their light travelled across enormous distances for billions of years. The Tarantula Nebula, meanwhile, sits only about 160,000 light-years away. That is still extremely far in human terms, obviously, but for astronomy, it is wonderfully close. Close enough for scientists to examine individual stars, close enough to map gas structures in detail, close enough to study how giant stars interact with surrounding clouds directly. It is like comparing satellite images of distant continents with walking through a nearby city street personally. The level of detail changes everything. One reason the James Webb Space Telescope became so important involves its ability to observe ancient galaxies directly in infrared light. Because the universe expands, light from distant galaxies stretches toward longer, redder wavelengths during its journey to Earth. This phenomenon, called redshift, effectively moves ancient ultraviolet and visible light into infrared wavelengths by the time we observe it. Webb was specifically designed to study such infrared signals, and what Webb found surprised astronomers repeatedly. Young galaxies in the early universe appeared brighter, more active, and more evolved than expected. Some formed stars at astonishing rates, shortly after cosmic dawn. Others already contained surprisingly organized structures. The universe matured quickly, and regions resembling the Tarantula Nebula may help explain how. If giant star-forming complexes became common in early galaxies, they could rapidly enrich surrounding space with heavy elements through supernovas and stellar winds. They could regulate star formation through radiation feedback. They could shape galactic evolution dramatically in relatively short cosmic timescales. The Tarantula Nebula essentially becomes a living experiment happening nearby. Astronomers can observe how massive stars sculpt their environments, how supernovas redistribute material, and how starburst activity unfolds across giant molecular clouds, and every observation helps refine models for ancient galaxies. Another fascinating connection involves reionization. Early in cosmic history, after the Big Bang, the universe cooled enough for neutral hydrogen atoms to form. Space eventually became filled with vast clouds of neutral hydrogen gas. Astronomers sometimes call this period the Cosmic Dark Ages, because no stars yet illuminated the universe significantly. Then the first stars and galaxies ignited. Their ultraviolet radiation gradually ionized surrounding hydrogen again, transforming the universe from mostly neutral into ionized plasma across enormous distances. This process, called cosmic reionization, changed the entire cosmos. Massive stars likely played central roles because they emit huge quantities of ultraviolet radiation capable of ionizing hydrogen. And the Tarantula Nebula demonstrates exactly how powerful such radiation fields become inside giant star-forming regions. The nebula glows intensely because giant stars continuously ionize surrounding hydrogen gas. Scaled upward across early galaxies, similar processes may have helped reionize much of the observable universe itself. In other words, Studying this nearby glowing cloud may help explain how the universe emerged from darkness billions of years ago. That is an extraordinary idea. Human beings built telescopes on one small planet, orbiting an ordinary star so they could study a nebula in a neighbouring galaxy to understand events from near the beginning of time itself. Astronomy constantly stretches the definition of ambition. Interestingly, the Tarantula Nebula also reveals how violent young galaxies probably were. People often imagine space as calm and silent. Ancient galaxies were likely anything but calm. Starburst activity generated enormous radiation fields. Supernovas erupted frequently. Stellar winds carved giant cavities through gas clouds. Shock fronts collided continuously. The Tarantula Nebula behaves similarly. It is crowded, turbulent, and unstable. Massive stars dominate the environment energetically. Giant cavities expand through surrounding gas. Radiation sculpts structures across hundreds of light years. Supernovas enrich the nebula chemically. And all of it unfolds relatively rapidly on cosmic timescales. The nebula essentially compresses many important astrophysical processes into one observable region. That makes it invaluable scientifically. Researchers use it to test models of stellar evolution, feedback mechanisms, galactic chemical enrichment, starburst behavior, and black hole formation. Even gravitational wave astronomy connects back indirectly. Massive stars inside clusters like R136 may eventually collapse into black holes capable of merging later. The violent stellar nurseries shaping early galaxies could also have produced many of the black hole systems modern detectors observe through gravitational waves today. Everything connects. Star formation influences supernovas. Supernovas influence chemistry. Chemistry influences planet formation. Black holes emerge from giant stars. Galaxies evolve through feedback from stellar populations. The Tarantula Nebula sits at the intersection of many of these processes simultaneously. And because it resembles conditions likely common long ago, astronomers keep returning to it repeatedly. The nebula almost functions like a bridge between local astronomy and cosmology, between nearby stars and the early universe, between detailed observations and ancient history. Another remarkable aspect involves just how temporary these extreme conditions are. The early universe eventually calmed somewhat. Galaxies aged, heavy elements accumulated, star formation rates changed, giant starburst regions became less dominant in many mature galaxies. Likewise, the Tarantula Nebula itself will not remain this violent forever. Eventually, enough giant stars will explode or disperse surrounding gas that current star formation activity will decline. The spectacular glowing structures visible today will evolve beyond recognition over millions of years. The nebula represents a phase, a brilliant turbulent moment inside a much longer galactic story. And perhaps that temporariness explains why astronomers find it so valuable. The Tarantula Nebula offers a rare nearby opportunity to observe conditions resembling ancient cosmic epochs that mostly vanished billions of years ago elsewhere. A surviving glimpse of younger, rougher stages in universal history, almost like discovering one active volcanic island, preserving geological conditions from Earth's distant past. Except the island spans hundreds of light years and contains stars large enough to terrify theoretical physics occasionally. And while the nebula helps explain the birth of galaxies and giant stars, it also raises another fascinating question. What happens after those massive stars die? Because inside the Tarantula Nebula, many future stellar corpses will not end as quiet remnants. Some may collapse into black holes born directly from the most violent stars in the nearby universe. Black holes are often described as monsters lurking in space, invisible, bottomless, hungry. The language sounds dramatic because human beings understandably struggle to discuss objects that trap light itself without becoming slightly theatrical. Still, the reality is stranger than most fiction. A black hole is not really a cosmic vacuum cleaner wandering around swallowing everything nearby. It is what happens when gravity wins completely, and inside the Tarantula Nebula, gravity is preparing to win many times over. The giant stars crowding regions like R136 are so massive that some will almost certainly end their lives by collapsing into black holes. Not eventually in the distant future of the universe, but relatively soon on cosmic timescales. Some may already have done so. That possibility makes the Tarantula Nebula more than just a spectacular stellar nursery. It may also be a factory for future black holes, including some massive enough to help explain the strange gravitational wave events astronomers have detected in recent years. To understand how black holes form from stars, we first need to revisit the final stages of massive stellar evolution. Ordinary stars survive through fusion. Hydrogen fuses into helium. Helium eventually fuses into heavier elements in larger stars. The energy released pushes outward against gravity. As long as fusion continues efficiently enough, the star remains stable. But fusion cannot continue forever. Eventually, giant stars develop iron-rich cores, and iron creates a fatal problem. Unlike lighter elements, iron fusion does not release usable energy. Once enough iron accumulates, the star can no longer support itself through fusion pressure. Gravity immediately takes over. The collapse happens violently and extremely fast. The core implodes inward at tremendous speeds. Electrons and protons combine into neutrons. Matter compresses to extraordinary densities. Then outcomes diverge depending on mass. Some collapsing stars form neutron stars, compact objects so dense that a teaspoonful would weigh billions of tons on Earth. But if the collapsing core contains enough mass, even neutron degeneracy pressure cannot stop gravity completely. The collapse continues, space-time curves more and more severely. Eventually an event horizon forms, and a black hole is born. Inside that boundary, gravity becomes so extreme that nothing escaping slower than light can leave again. Since light itself cannot escape, the black hole appears dark against surrounding space, hence the name. Interestingly, black holes themselves are not actually holes in the usual sense. They are regions where mass becomes compressed into extraordinarily small volumes relative to their gravitational influence. The mathematics describing their interiors eventually breaks down into singularities, places where current physics stops behaving sensibly, which is usually a sign scientists need better equations. Still, the external behaviour of black holes follows relativity remarkably well, and the Tarantula Nebula likely contains many future examples waiting to form. The stars inside R136 are especially important because some possess enormous masses even after losing material through stellar winds. When such stars collapse, they may produce relatively large black holes directly. That matters because astronomers recently discovered something unexpected. Gravitational wave observatories like LIGO and Virgo detected black hole mergers involving surprisingly massive black holes. Some measured dozens of solar masses each, larger than many earlier models predicted should commonly form from stars. Scientists immediately began asking where such black holes came from. The Tarantula Nebula may provide part of the answer. Low metallicity environments influence stellar evolution significantly. Remember, the Large Magellanic Cloud contains fewer heavy elements than the Milky Way. Lower metallicity weakens stellar winds because radiation-driven outflows depend partly on heavy elements. Weaker winds mean giant stars lose less mass before collapse, and that means they may leave behind larger black holes. In simple terms, stars inside places like the Tarantula Nebula may die heavier. Astronomers suspect many black holes detected through gravitational waves may have originated in environments similar to this one. That connection transformed giant stellar nurseries from visually impressive objects into crucial laboratories for understanding black hole populations across the universe. And the process does not end with formation alone. Dense star clusters like R136 create ideal environments for gravitational interactions. Black holes born inside crowded clusters may encounter one another repeatedly, Some form binary systems. Others exchange partners dynamically through close interactions with neighbouring stars and black holes. Eventually, two black holes may spiral inward and merge. When that happens, space-time itself ripples outward, literally. Einstein predicted gravitational waves over a century ago as part of general relativity. Massive accelerating objects should distort space-time, generating waves travelling outward at light speed. For decades, those waves remained theoretical because detecting them seemed almost impossible. The distortions are tiny beyond ordinary comprehension. LIGO eventually succeeded by measuring changes smaller than atomic nuclei across instruments kilometers long. And what it detected changed astrophysics permanently. Black hole mergers, violent collisions releasing enormous energy through gravitational waves alone. For brief moments, merging black holes can emit more power than all the stars in the observable universe combined, not in light, but in space-time distortion itself. And some of those black holes may have begun life inside violent stellar nurseries resembling the Tarantula Nebula. That idea feels almost poetic despite being entirely physical. Massive stars form in turbulent clouds. They flood their surroundings with radiation. They explode or collapse. Black holes emerge. Millions or billions of years later, those black holes collide and shake space-time across the cosmos. The consequences of stellar birth ripple forward for unimaginable spans of time. One especially fascinating possibility involves direct collapse. Some extremely massive stars may not explode traditionally at all. Instead of producing powerful visible supernovas, the core collapses so completely that much of the star falls inward directly into a black hole. Astronomers sometimes call these failed supernovas, which sounds slightly unfair because forming a black hole still seems like a rather committed effort overall. But compared to brilliant supernova explosions, the visual display may indeed appear weaker or absent. The star simply vanishes gradually as collapse proceeds. Imagine watching one of the brightest stars in a galaxy suddenly disappear without dramatic fireworks. The universe occasionally prefers unsettling subtlety. Inside the Tarantula Nebula, some stars may eventually experience exactly that fate. Others may produce gamma-ray bursts. These events rank among the most energetic explosions known in the universe. Under certain conditions, collapsing massive stars generate narrow relativistic jets blasting outward near light speed. If one jet points toward Earth, astronomers observe an intense burst of gamma radiation. Fortunately, the Tarantula Nebula lies safely far away, because nearby gamma-ray bursts could prove catastrophic for planetary atmospheres and life. Distance remains one of humanity's best survival strategies in astronomy. Still, even from afar, the black hole formation process inside the Tarantula Nebula matters enormously for understanding cosmic evolution. Black holes influence surrounding environments dramatically. Matter falling toward them heats up intensely in accretion disks. Magnetic fields twist around in flowing material. Jets may erupt outward. X-rays and high-energy radiation emerge from accreting systems. In binary star systems, black holes may slowly siphon material from companion stars. The infalling gas heats to extraordinary temperatures before crossing the event horizon, creating luminous X-ray sources detectable across galaxies. Some such systems likely already exist inside the Large Magellanic Cloud. Astronomers have identified several black hole candidates there through X-ray observations and stellar motion measurements. Even invisible objects reveal themselves through gravity eventually. That is one of the strange beauties of astronomy. Humans cannot see black holes directly because no light escapes them, yet astronomers still study them successfully by observing how they affect surrounding matter and space-time. Stars orbit unseen masses, gas heats while falling inward, gravitational waves ripple outward from mergers, the invisible becomes measurable through consequences, and the Tarantula Nebula may eventually produce many such consequences. The environment there practically encourages extremes. Massive stars form abundantly, clusters remain crowded, low metallicity alters stellar evolution, radiation and stellar winds reshape surrounding gas, supernovas enrich the environment chemically, black holes emerge from collapsed cores, everything feeds into everything else. The nebula behaves less like an isolated object, and more like an interconnected cosmic engine, continuously recycling matter and energy through different states. One particularly strange implication involves future generations of stars. Material expelled through supernovas and stellar winds eventually mixes into surrounding clouds. New stars form partly from that enriched matter. Some future planetary systems may therefore contain atoms once passing through giant stars inside regions like the Tarantula Nebula. Perhaps somewhere billions of years from now, living organisms on distant planets will contain calcium or iron forged by stars currently shining inside R136. The universe recycles aggressively. Even black holes participate indirectly. Although matter crossing event horizons disappears from ordinary observation, black holes influence galactic evolution through gravity and energetic feedback. Supermassive black holes at galactic centers regulate star formation across enormous scales through jets and radiation. Stellar mass black holes formed inside nebulae like the Tarantula may eventually contribute to larger structures and interactions over cosmic time. Nothing remains isolated forever, and the Tarantula Nebula demonstrates that beautifully. Every giant star there already affects neighbouring clouds through radiation and winds. Future supernovas will spread heavy elements. Black holes may emerge from collapsed cores. Binary systems may merge. Gravitational waves may travel across billions of light years, all from one violent region inside a neighbouring galaxy. Another fascinating aspect involves uncertainty. Astronomers still do not fully understand every detail of massive star collapse. Exactly how different stars explode, fail to explode, or produce black holes remains an active area of research. Rotation matters, magnetic fields matter, mass loss matters, binary interactions matter enormously too. Many giant stars exist in binary or multiple systems. Close companions can exchange material, alter rotation rates, or even merge entirely before collapse. Inside crowded clusters like R136, such interactions may become especially important. Theoretical models continue evolving as observations improve, and the James Webb Space Telescope may help enormously by revealing hidden stellar populations and environments inside dense star-forming regions. Infrared observations penetrate dust clouds previously obscuring key details. Young massive stars, embedded protostars, and complex gas structures become visible more clearly. The deeper humanity looks into the Tarantula Nebula, the more complicated the situation appears, which is usually how astronomy progresses. Every major technological improvement reveals the universe behaving in ways slightly stranger than expected. Still, one conclusion remains unavoidable. The Tarantula Nebula is not merely producing stars, it is producing future catastrophes, future supernovas, future neutron stars, future black holes, future gravitational wave sources. The region functions like a cosmic forge where matter passes through increasingly extreme states over relatively short cosmic timescales. And amid all this violence, one oddly peaceful question remains. Could planets ever survive in such an environment? Planet formation is already a surprisingly delicate process under normal conditions. That may sound odd considering planets themselves can become enormous. Jupiter contains enough mass to fit more than 1,300 Earths inside it. Giant exoplanets larger than Jupiter orbit countless stars throughout the galaxy. Even rocky planets like Earth required staggering amounts of material to assemble over millions of years. Still, the process begins gently. Tiny dust grains drifting through disks around young stars collide and stick together gradually. Microscopic particles become pebbles, pebbles become rocks, rocks merge into planetesimals. Over immense spans of time, gravity pulls larger bodies together into planets. At least that is the simplified version. In reality, planet formation involves turbulence, collisions, migration, magnetic fields, temperature gradients, and enough unanswered questions to keep astronomers happily employed for several lifetimes. And all of that complexity assumes the environment remains relatively calm. The Tarantula Nebula is not calm. Trying to form planets, they may resemble attempting to build a snowman beside an active volcano during a hurricane while someone repeatedly detonates fireworks nearby for several million years. Possible perhaps in isolated cases, but certainly difficult. That is what makes the Tarantula Nebula so fascinating from a planetary perspective. Astronomers know stars are forming there abundantly. The question becomes whether stable planetary systems can survive the violent conditions surrounding those newborn stars. The answer appears complicated. To understand why, we first need to revisit how planets normally form around stars. Young stars often emerge surrounded by rotating disks of gas and dust called protoplanetary disks. These disks contain leftover material from the star formation process. Over time, particles inside the disk collide and gradually assemble into planets, moons, asteroids, and comets. The process takes millions of years, and critically, the disk must survive long enough for planets to grow. Inside relatively peaceful regions of the Milky Way, many disks endure for several million years before dispersing. That gives rocky planets enough time to begin forming and giant planets enough opportunity to gather thick gas envelopes. But inside the Tarantula Nebula, giant stars create serious problems almost immediately. The first issue is ultraviolet radiation. Massive stars emit enormous quantities of energetic ultraviolet light capable of ionizing gas and heating surrounding material dramatically. When this radiation strikes nearby protoplanetary disks, it can photo-evaporate them, essentially heating gas enough that it escapes into surrounding space. Imagine trying to fill a swimming pool while someone continuously drills holes in the sides. The disk loses material faster than normal, and because giant stars inside the Tarantula Nebula often exist crowded together in clusters, nearby young stars may get exposed to multiple intense radiation sources simultaneously. Some disks probably erode rapidly. Astronomers actually observe similar processes inside smaller stellar nurseries closer to Earth. In the Orion Nebula, for example, Hubble images revealed structures called proplids, young disks around stars, being blasted by ultraviolet radiation from nearby massive stars. The disks glow brightly where radiation strikes them. Some develop comet-like tails streaming away from intense stellar radiation. And the Orion Nebula is comparatively gentle beside the Tarantula Nebula. Conditions inside R136 and surrounding regions become far harsher. Ultraviolet radiation floods enormous volumes of space. Stellar winds collide violently with surrounding gas. Shock fronts ripple continuously through the environment. Planet formation. There may become a race against destruction. Another problem involves stellar density. Inside crowded star clusters, stars pass relatively close to one another compared to the quiet isolation surrounding the Sun. Gravitational interactions between nearby stars can disrupt planetary systems or distort protoplanetary disks. If another star passes close enough, it may destabilize planetary orbits or strip material from disks entirely. The solar system developed in a fairly spacious neighborhood. The nearest star today remains over 4 light-years away. That distance provides stability. Gravitational disturbances from neighboring stars stay weak most of the time. Inside dense regions of the Tarantula Nebula, stars crowd much closer together. The night sky from a hypothetical planet there would probably appear astonishingly bright. Some neighbouring stars could outshine Earth's full moon permanently. Radiation from nearby giants would dominate the environment continuously. Beautiful perhaps, but not ideal for stable planetary development. Then there are supernovas. Massive stars inside the Tarantula Nebula live short lives. Some explode within only a few million years after formation. Their shockwaves and radiation can dramatically affect surrounding systems, A nearby supernova might strip atmospheres from planets, irradiate surfaces heavily, or disrupt fragile protoplanetary disks still forming. Again, timing matters enormously. Rocky planets require time to assemble gradually through countless collisions and accretion events. Giant planets need enough surviving gas to form thick atmospheres before stellar radiation disperses the disk. Inside violent starburst regions, that timeline may become difficult to maintain, and yet astronomers hesitate to conclude planet formation becomes impossible there, because the universe repeatedly demonstrates remarkable resilience. Even inside harsh environments, some disks may survive partially shielded by dense gas clouds or favourable locations farther from giant stars. Lower mass stars continue forming throughout the nebula. Not every star emerges directly beside hypermassive giants. Some planetary systems may therefore persist despite the surrounding chaos. Actually, giant star-forming regions may produce enormous numbers of stars overall, meaning even low survival percentages could still yield many planetary systems eventually. The conditions simply become more dangerous and unpredictable. One especially interesting question involves habitability. Suppose planets do form successfully inside or near regions like the Tarantula Nebula. Could life ever emerge there? At first glance, the answer seems discouraging. Massive stars live briefly. Many emit intense ultraviolet radiation harmful to biological molecules. Nearby supernovas create additional hazards. Frequent gravitational disturbances inside crowded clusters may destabilize planetary orbits over time, and yet habitability in astronomy often surprises researchers. Life on Earth proved remarkably adaptable. Organisms survive near deep-sea hydrothermal vents, inside Antarctic ice, beneath deserts, and in highly radioactive environments. Still, there may be limits. A planet orbiting too close to giant stars inside R136 would likely experience sterilizing radiation continuously. Atmospheres might erode under intense ultraviolet bombardment. Nearby supernovas could periodically flood surfaces with energetic particles. The neighborhood would not feel welcoming. Perhaps the best comparison involves weather. Some places on Earth experience calm, stable climates favorable for long-term biological complexity. Others suffer constant hurricanes, volcanic eruptions, or environmental extremes. The Tarantula Nebula resembles cosmic extreme weather. Planets might form there occasionally, but surviving comfortably for billions of years becomes more difficult. Another challenge involves time itself. Massive stars evolve quickly. Regions dominated by giant stars change dramatically over relatively short cosmic timescales. Radiation fields shift, supernovas erupt, gas disperses, star clusters expand gradually as stars move over time. The environment does not remain stable long enough for slow biological evolution around giant stars directly. Earth required billions of years for complex life to emerge. Most massive stars inside the Tarantula Nebula will explode long before reaching such ages. That suggests lower mass stars become more promising candidates for eventual habitability there. Red dwarfs and sun-like stars survive far longer. If they form in quieter outer regions or eventually drift away from violent cluster centers, their planetary systems might stabilize later. In fact, many stars born in dense clusters eventually disperse into broader galactic environments. The Sun itself may have formed inside a larger stellar nursery billions of years ago, before drifting into its current relatively peaceful region of the Milky Way. Astronomers suspect nearby supernovas may even have influenced early solar system chemistry. Certain radioactive isotopes found in meteorites hint that massive stars existed near the Sun's birth environment, so the Tarantula Nebula may not represent an impossible birthplace for planetary systems, just a dangerous one. Some stars born there today might eventually wander into calmer galactic regions carrying planetary systems with them. Billions of years later, those systems could appear completely ordinary despite their violent origins. That idea feels strangely comforting somehow. Even peaceful worlds may emerge from turbulent beginnings. The chemistry of planet formation also becomes interesting in giant star-forming regions. Massive stars enrich surrounding gas rapidly through stellar winds and supernovas. Heavy elements required for rocky planets spread throughout the nebula. Carbon, oxygen, silicon, iron, magnesium, all essential building materials for terrestrial worlds, become increasingly available. In one sense, giant stars help make planets possible chemically. Without previous generations of massive stars, rocky planets like Earth could not exist at all. The same explosions threatening young planetary systems also create the heavy elements future planets require. Creation and destruction remain intertwined again. Astronomy rarely allows simple answers. One process destroys disks, another enriches future star-forming clouds. One supernova sterilizes nearby environments, another scatters materials necessary for biology later elsewhere. The universe operates through cycles rather than clean separations between good and bad outcomes. Interestingly, the James Webb Space Telescope may help answer some of these questions directly. Webb's infrared instruments allow astronomers to study young disks hidden within dusty star-forming regions more effectively than ever before. Researchers can examine how radiation affects disk survival, chemistry, and structure under extreme conditions. Already Webb has revealed extraordinary detail inside stellar nurseries throughout the cosmos, and the Tarantula Nebula remains one of its most important targets, because ultimately the question extends beyond planets alone. Astronomers want to understand how common planetary systems truly are across different galactic environments. Do planets form almost everywhere stars do? Or do violent regions suppress them significantly? Can stable worlds emerge from starburst environments? The Tarantula Nebula offers crucial clues, and the answers matter philosophically too. Humanity spent most of history wondering whether planets existed around other stars at all. Now astronomers know planets are incredibly common throughout the galaxy. Thousands of exoplanets already fill scientific catalogues. Some orbit binary stars, some circle pulsars, some drift freely through space without parent stars. Nature appears remarkably willing to build worlds under strange conditions. So perhaps even the Tarantula Nebula eventually produces planets, despite all the violence surrounding their birth. Still, the environment there remains extraordinary. Imagine standing on a hypothetical planet inside a dense region near R136. The sky might never become truly dark. Nearby giant stars would blaze overhead continuously, flooding the landscape with strange light. Supernovas might occasionally rival suns in brightness temporarily. Radiation storms could ripple through surrounding space regularly. The heavens would feel alive in ways Earth's calm night sky rarely does. Beautiful perhaps, terrifying certainly, and temporary, because giant star clusters evolve quickly. Over millions of years, supernovas and stellar winds gradually disperse surrounding gas. Massive stars die, clusters expand, the violent heart of the nebula changes. The Tarantula Nebula itself will not remain in its current state forever, but while it exists, it provides astronomers with one of the most extraordinary natural laboratories in the nearby universe. A place where stars form violently, giant suns reshape entire regions of space, black holes begin their existence, and planets may struggle to survive amid the chaos. And recently, humanity gained its clearest view yet into that chaos through a telescope specifically designed to peer through cosmic dust itself. When the James Webb Space Telescope finally began observing the universe, astronomers immediately pointed it towards some of the most dramatic places they could think of. Naturally, the Tarantula Nebula made the list almost immediately. That decision was not simply because the nebula looks spectacular in photographs, although it certainly does. Scientists targeted it because Webb possesses abilities previous telescopes lacked, especially when it comes to seeing through dust, and the Tarantula Nebula contains dust everywhere. Gigantic dark clouds snake through glowing hydrogen regions. Dense cocoons surround forming stars. Entire structures remain partially hidden behind thick curtains of interstellar material. Visible light telescopes like Hubble revealed astonishing detail there already, but infrared observations promise something even more valuable. Webb could look inside the storm. That capability matters because dust creates one of astronomy's strangest paradoxes. Dust both hides and reveals cosmic evolution simultaneously. In visible light, dense dust clouds appear dark because they absorb and scatter shorter wavelengths. Regions packed with gas and dust often conceal the very stars forming within them. But infrared light behaves differently. Longer wavelengths penetrate dust far more effectively. Infrared telescopes can therefore peer into stellar nurseries, invisible in ordinary visible light. Structures previously obscured suddenly emerge. Hidden protostars become visible. Complex cloud geometries appear in extraordinary detail. The James Webb Space Telescope was designed precisely for this kind of work. Its enormous segmented mirror collects faint infrared signals with remarkable sensitivity. Its instruments analyze wavelengths impossible for human eyes to detect directly. And because Webb operates far from Earth, shielded carefully from heat, it can observe extremely faint infrared sources without interference. When astronomers turned Webb toward the Tarantula Nebula, the results immediately became some of the most extraordinary images ever captured of a stellar nursery. Not merely beautiful, informative. The telescope revealed intricate structures hidden within dusty clouds across the nebula. Dense filaments twisted through space like tangled smoke illuminated from within. Cavities carved by stellar winds appeared sharper and more complex than expected. Young stars previously concealed behind dust emerged throughout the region. The nebula suddenly looked deeper, richer, more crowded. One of Webb's early images focused on a region nicknamed the Cosmic Tarantula's Burrow, a dramatic cavity inside the nebula shaped partly by radiation and stellar winds from massive stars. The image revealed countless background galaxies visible through gaps in the nebula material itself, an almost unsettling reminder that even this enormous cloud represents only one structure within a much larger universe. That visual layering felt extraordinary. Nearby gas clouds glowing violently in one galaxy, ancient galaxies shining faintly billions of light years farther behind them. Different eras of cosmic history stacked together inside one telescope image. And the closer astronomers looked, the stranger the Tarantula Nebula became. Webb exposed previously hidden protostars still embedded inside dense, dusty cocoons. These young forming stars remained difficult or impossible to study clearly before, because visible light could not penetrate the surrounding material effectively. Now researchers could examine where stars were still actively forming despite the nebula's violent conditions. That mattered enormously. For years, astronomers debated how stellar feedback from giant stars influences nearby star formation. Radiation, stellar winds, and supernovas clearly disrupt surrounding clouds, but do they mostly suppress new stars or trigger them? Webb's observations provided fresh clues. Some regions showed evidence of compression, where stellar feedback may actually encourage gravitational collapse in neighbouring clouds. Dense knots appeared poised for future star formation, despite nearby radiation fields. The nebula behaves less like a simple, destructive environment, and more like a constantly evolving chain reaction. One generation of stars disrupts clouds while helping create conditions for another generation elsewhere, and Webb could finally observe parts of that process directly in unprecedented detail. Another major discovery involved the complexity of dust itself. Dust grains inside the Tarantula Nebula do not distribute evenly. Some regions contain thick concentrations capable of shielding material from intense ultraviolet radiation temporarily. Others appear shredded and sculpted by nearby giant stars, Infrared imaging revealed layered structures within dust clouds that previously looked almost featureless in visible light. The nebula became topographical somehow, like mountains and valleys carved into interstellar matter by radiation instead of erosion. Astronomers also used Webb's spectroscopic instruments to analyze the chemistry inside different regions. Spectroscopy allows scientists to split light into component wavelengths, revealing fingerprints from specific atoms and molecules. Every element leaves characteristic patterns: hydrogen, carbon, oxygen, nitrogen, complex molecules, all identifiable through spectral signatures. Inside the Tarantula Nebula, Webb detected intricate chemical structures across star-forming regions, helping astronomers trace how stellar radiation alters surrounding material. And because the nebula resembles ancient starburst environments, every new detail potentially improves understanding of the early universe too. That connection remained one of Webb's central scientific goals from the beginning. The telescope was built partly to study cosmic dawn, the era when the first stars and galaxies formed after the Big Bang. But distant ancient galaxies remain difficult to observe clearly even with Webb's extraordinary sensitivity. The Tarantula Nebula provides something complementary, a nearby analogue, a local environment where scientists can study intense star formation directly at much higher resolution than possible for ancient galaxies. It is almost like comparing satellite images of a distant storm with walking into a nearby hurricane personally. Both observations matter. Together they improve understanding enormously. One especially fascinating result involved just how chaotic the nebula's interior truly is. Earlier images already showed dramatic structures, but Webb revealed turbulence and fragmentation on smaller scales throughout the clouds. Dense filaments branch repeatedly, cavities overlap, dust structures appear, shredded and reshaped by multiple interacting forces simultaneously. The nebula does not look engineered. It looks alive with motion. Again, not biologically alive, obviously. The Tarantula Nebula is not conscious. It has no awareness whatsoever, but the processes unfolding there are dynamic enough that still images almost feel misleading. If humans could watch the nebula evolve over millions of years in accelerated time, the structures would probably appear restless and unstable. Clouds collapsing, shock fronts expanding, pillars evaporating, stars igniting, cavities widening. Webb's images captured frozen moments inside that turbulence with astonishing clarity, and clarity changes perspective. Before infrared astronomy matured, much of the Tarantula Nebula appeared dominated mainly by bright visible structures shaped by giant stars. Webb revealed how much activity remained hidden inside darker regions too. Some of the most important processes in astronomy occur behind dust. Stars form buried within dense clouds because those environments shield collapsing gas from external radiation long enough for gravity to work effectively. Planet-forming disks surround young stars within dusty regions. Complex chemistry develops inside protected molecular clouds. Dust both conceals and protects, and Webb specializes in peering through it. Another remarkable aspect of the observations involved scale. The Tarantula Nebula already spans roughly 1,000 light-years. Webb revealed fine structures embedded within that enormous volume, tiny details nested inside giant systems. Astronomy often works this way. Immense scales contain delicate complexity. A cloud hundreds of light-years wide may still contain intricate filaments smaller than the solar system. Giant star clusters influence environments across enormous distances, while individual protostars quietly form inside dense, isolated pockets nearby. The universe rarely behaves uniformly, and Webb's observations highlighted that beautifully. Some regions inside the nebula appear almost sterilized by intense radiation from nearby massive stars. Others remain heavily obscured and active with ongoing star formation. Dense pillars survive temporarily beside expanding cavities. Everything depends on local conditions. distance from giant stars, density of surrounding gas, magnetic fields, shockwave interactions, chemical composition. The Tarantula Nebula becomes a giant astrophysical ecosystem of competing influences. One particularly exciting possibility involves understanding the formation of massive stars themselves. Astronomers still do not fully understand how stars exceeding 100 solar masses form without radiation halting accretion. Webb's observations of embedded massive protostars and surrounding gas flows may help answer some of those questions. Do giant stars form through mergers, through highly focused accretion disks, through dense filamentary inflows? Perhaps several mechanisms operate simultaneously. The nebula continues refusing to simplify itself conveniently for human understanding, and that refusal is precisely why astronomers adore it. Complicated systems reveal physics more honestly. Another fascinating Webb result involved background galaxies visible through thinner parts of the nebula. Infrared sensitivity allowed the telescope to detect ancient galaxies far beyond the Large Magellanic Cloud itself. That layering created a strange visual effect. Nearby star formation, distant galactic evolution, ancient cosmic history, all visible together. The Tarantula Nebula almost became transparent enough to reveal the deep universe hiding behind it, which feels oddly symbolic somehow. The closer humanity examines one violent stellar nursery, the more it uncovers connections stretching across cosmic history itself. Webb also highlighted how important stellar feedback becomes in shaping galaxies overall. Massive stars do not merely exist inside nebulae passively. Their radiation and winds regulate future star formation, alter gas distributions, and influence galactic evolution across enormous scales. The Tarantula Nebula provides one of the clearest nearby demonstrations of this process operating intensely. Young, massive stars carve cavities. Shock fronts compress neighbouring clouds. Supernovas enrich the environment chemically. New stars form partly from material processed by earlier generations. Galaxies evolve through feedback loops driven partly by stars like these. And Webb's observations made those interactions more visible than ever before. One surprising emotional effect of Webb imagery involved texture. The nebula suddenly appeared tactile somehow. Dust structures looked layered and folded. Gas clouds resembled smoke illuminated by hidden fires. Cavities felt hollowed and deep rather than flat. People reacted strongly because the images seemed simultaneously alien and familiar. Storm clouds, ocean currents, flames, tree roots. Human brains search constantly for recognizable patterns. The Tarantula Nebula offers many. But beneath the visual familiarity lies an environment utterly hostile to human survival. Temperatures in ionized regions exceed thousands of degrees. Radiation levels near giant stars become instantly lethal. Shockwaves and stellar winds race through surrounding space continuously. Beauty in astronomy frequently emerges from violent conditions, and perhaps no nearby region demonstrates that more effectively than the Tarantula Nebula under Webb's gaze. Still, for all the scientific value of the observations, the images also accomplished something less measurable. They reminded people how astonishing the universe actually is. A neighbouring galaxy contains a giant glowing web where stars larger than anything humans once imagined blast radiation through clouds spanning hundreds of light years. Black holes may already be forming there. Future supernovas wait ahead. Entire regions shift under the pressure of stellar winds and gravity, and somehow, tiny creatures on one planet built a telescope capable of examining those structures across 160,000 light-years of space. That achievement alone feels almost improbable. The Tarantula Nebula is easy to think of as something distant, a violent cloud in another galaxy, a strange glowing structure hanging far beyond human life and human history. And technically, that is true. The nebula sits roughly 160,000 light-years away inside the Large Magellanic Cloud. Its giant stars will never visit Earth. Its supernovas cannot harm us from that distance. The radiation flooding through its clouds remains separated from humanity by incomprehensible stretches of space. Yet the more astronomers study the Tarantula Nebula, the harder it becomes to treat it as completely unrelated to us. Because hidden inside that violent stellar nursery are clues about how everything around us came to exist in the first place. Not metaphorically, literally. The atoms making up Earth, oceans, mountains, plants, animals, and human beings all originated through processes connected to environments like this one. And that realization changes the nebula entirely. It stops being merely an astronomical object. It becomes part of our own history. To understand why, we need to think about the early universe again. After the Big Bang, the cosmos remained chemically simple. Hydrogen dominated. Helium followed behind. Tiny traces of lithium existed too, but not much else. No oxygen, no carbon, no iron, no silicon, no calcium, no phosphorus. None of the heavier elements required for rocky planets or biology had formed yet. The universe began astonishingly empty from a chemical perspective. Then stars appeared. Gravity gathered gas into collapsing clouds. Nuclear fusion ignited. The first generations of stars began manufacturing heavier elements inside their cores. Massive stars especially transformed the cosmos rapidly. Their enormous temperatures and pressures allowed fusion to create increasingly complex atoms. Carbon emerged. Oxygen followed. Silicon, sulfur, neon, magnesium, and eventually iron formed through stellar nucleosynthesis. And when giant stars exploded, those elements scattered into surrounding space. The universe slowly became enriched. Future generations of stars formed from gas clouds containing heavier elements produced by earlier stars. Planetary systems emerged from enriched material. Rocky worlds became possible because ancient stars had already lived and died beforehand. The Tarantula Nebula demonstrates this process happening vividly. Inside its glowing clouds, giant stars manufacture heavy elements continuously. Stellar winds scatter material into surrounding regions. Supernovas enrich the nebula further. New stars form partly from matter processed through previous generations. The cycle repeats. One generation creates conditions for the next. Astronomy often feels abstract until you realize the process includes us too. Human beings exist because earlier stars enriched the universe chemically long before the sun formed. Every carbon atom in your body passed through stellar interiors somewhere in cosmic history. The oxygen you breathe, the calcium in your bones, the iron carried through your bloodstream, all forged through nuclear fusion or stellar explosions billions of years ago. When astronomers say humans are made of stardust, they are not speaking poetically. They are describing astrophysical recycling, and the Tarantula Nebula offers a visible example of that recycling still unfolding. The region resembles a giant cosmic foundry where matter cycles through different forms repeatedly. Clouds collapse into stars. Stars create heavy elements. Radiation and explosions scatter material outward. New clouds form later from enriched debris. Over immense timescales, that process builds galaxies capable of producing planets and eventually life. Without massive stars, the universe would remain chemically primitive forever. There would be no rocky planets, no oceans, no DNA, no observers studying nebulae. That alone makes places like the Tarantula Nebula deeply important. Even more fascinating, our solar system may itself have formed in an environment not entirely unlike this one, though probably less extreme. Astronomers suspect the Sun was born inside a larger stellar nursery containing many sibling stars. Certain radioactive isotopes found in ancient meteorites hint that nearby supernovas influenced the young solar system, shortly before or during its formation. For example, isotopes like aluminum-26 decay relatively quickly in cosmic terms. Their presence in early solar system material suggests fresh stellar debris entered the region not long before planets began assembling. A nearby massive star may therefore have exploded close to the Sun's birth environment. Perhaps a supernova shockwave even helped trigger the collapse of the molecular cloud that formed the solar system in the first place. In that sense, humanity's existence may connect indirectly to ancient stellar violence. The calm, stable environment Earth experiences today emerged from much rougher beginnings long ago. And the Tarantula Nebula shows those beginnings still happening elsewhere. Of course, the nebula itself is more extreme than the Sun's likely birthplace. R136 contains stars vastly larger than the Sun ever was. Radiation levels there become extraordinary, stellar densities rise much higher. Still, the underlying physics remains familiar. Gravity gathers matter, stars form, heavy elements emerge, supernovas scatter enriched material, planets eventually appear. The same universal processes repeat across galaxies. Another remarkable thing the Tarantula Nebula reveals involves scale. Human beings naturally think locally. We evolved around landscapes, weather, seasons, and ordinary physical distances. Our instincts rarely prepare us for thinking about events unfolding across hundreds of light years, over millions of years. Yet astronomy forces perspective changes constantly. The Tarantula Nebula spans roughly 1,000 light-years. Inside it, giant stars emit more energy in seconds than human civilization has consumed across all of recorded history. Supernovas reshape entire regions of space. Black holes may already be forming. Shockwaves travel through clouds for tens of thousands of years. And somehow all of it contributes eventually to the creation of ordinary things. Rocks, water, atmospheres, planets, biology. It is difficult to overstate how strange that chain of events really is. Matter forged inside exploding stars billions of years ago eventually assembled into living organisms capable of asking where that matter came from. The universe became aware of itself through recycled stellar debris. That realization affects many astronomers deeply, even highly technical researchers. Because the Tarantula Nebula transforms from a distant object into part of a much larger story about cosmic evolution itself, and importantly, that story remains unfinished. Stars continue forming there right now. Future supernovas will enrich surrounding gas further. New stellar systems may emerge from material already processed through earlier generations. Perhaps rocky planets will eventually form around quieter stars drifting away from the nebula's violent core. Maybe billions of years from now, some distant civilization will look toward the remnants of the Tarantula Nebula and wonder about its role in their own origins too. The idea sounds speculative, but the chemistry itself is inevitable. Heavy elements produced there will eventually spread through surrounding galactic environments. Matter keeps moving. Galaxies recycle material continuously. Even our own bodies participate in similar cycles on Earth. Atoms move through air, oceans, soil, plants, animals, and ecosystems constantly. The universe simply operates that recycling process on vastly larger scales. One particularly beautiful aspect of the Tarantula Nebula involves impermanence. The structures humans admire today will not last forever. The glowing filaments, the giant cavities, the spider-like shape, all temporary. Over millions of years, stellar winds and supernovas will disperse much of the gas. Massive stars will die. The nebula's appearance will change dramatically. Eventually, the current structure may vanish almost entirely. But disappearance does not mean failure. The nebula exists to transform matter, to process gas into stars and stars into heavier elements, to create future possibilities elsewhere. Astronomy often reveals that destruction and creation are not opposites. They are phases. A supernova destroys a star while creating the conditions for future planets. Radiation erodes clouds while triggering collapse elsewhere. Black holes emerge from stellar death while influencing future galactic evolution. The Tarantula Nebula embodies that cycle continuously, and perhaps that is why humans find such places emotionally compelling even beyond scientific curiosity. We recognize something familiar there. not visually perhaps, but structurally. Human life also emerges through cycles of transformation. Generations overlap. Old structures disappear while new ones form. Matter and energy move continuously through systems larger than individual lives. The universe operates similarly at every scale. Another fascinating implication involves rarity. For most of cosmic history, the universe lacked the chemical richness necessary for life as humans understand it. The earlier stars lived and died before rocky planets became common. Heavy elements accumulated gradually over billions of years. That means life capable of observing nebulae likely required long chains of stellar evolution beforehand. The Tarantula Nebula therefore represents not only cosmic violence, but cosmic preparation. Future generations of stars forming from its enriched material may possess planetary systems impossible during the universe's earliest eras. In a sense, giant stellar nurseries help make complexity possible, and complexity eventually produces observers. That progression still feels astonishing no matter how many times astronomy demonstrates it. Tiny fluctuations in early hydrogen gas after the Big Bang eventually led to galaxies, giant stars, heavy elements, planets, oceans, cells, ecosystems, consciousness, and telescopes studying distant nebulae. The chain stretches across nearly 14 billion years, and the Tarantula Nebula occupies one vivid part of that chain. Another thing the nebula reveals is how interconnected cosmic evolution truly is. Human beings sometimes imagine stars, planets, and galaxies as separate topics. In reality, they constantly influence one another. Stars shape galaxies through radiation and supernovas. Galaxies shape star formation through gravity and gas flows. Planets emerge from stellar debris. Black holes influence galactic structure. Nothing evolves independently. The Tarantula Nebula makes those connections visible. You can almost watch cosmic evolution happening there in real time, at least as close to real time as astronomy allows. Clouds collapsing, massive stars reshaping their surroundings, heavy elements spreading outward, future stellar systems waiting inside dense, dusty regions. The universe building itself continuously. And remarkably, humans arrived at a moment in history when technology finally became capable of studying such processes directly. For thousands of years, nebulae appeared only as faint smudges in the sky. People could admire them but not truly understand them. Now, telescopes like Hubble and Webb reveal stellar nurseries in extraordinary detail. Spectroscopy measures chemical compositions across distant clouds. Infrared imaging peers through dust to observe hidden protostars. Gravitational wave detectors listen for black hole mergers born from massive stars. Humanity became capable of tracing its own cosmic ancestry scientifically. That may be one of civilization's greatest achievements. Not merely building powerful technology, but using it to understand where the material making up life itself originated. And the Tarantula Nebula remains one of the clearest nearby demonstrations of those origins still unfolding. A violent, glowing reminder that creation in the universe rarely happens gently. Stars must burn, clouds must collapse, supernovas must explode, black holes must form, matter must cycle endlessly through destruction and renewal. Only then do planets and living worlds eventually emerge, and somewhere inside that immense chain of events, one small species on one small planet learned to look upward and recognize itself in the stars. So now, after travelling through collapsing clouds, giant stars, supernovas, black holes, radiation storms and cosmic webs stretching across another galaxy, the Tarantula Nebula begins to feel a little different than it did at the start of our journey. At first, it may have sounded like simply another beautiful object in space, a dramatic photograph, a colourful cloud with an intimidating name attached to it. But the deeper we drifted into it, the stranger it became. The Tarantula Nebula is not a static object hanging quietly in the dark. It is a place where the universe is actively transforming itself. Stars are being born there right now. Some are already dying. Others may collapse into black holes long before Earth's continents change shape again. Shockwaves continue moving through clouds. Radiation reshapes entire regions of gas. Heavy elements spread outward into future generations of stars and planets. Nothing inside the nebula truly rests, and yet somehow, from far away, it still appears peaceful. That contrast says something interesting about astronomy itself. The universe often looks calm because humans observe it across very short timescales. A nebula photographed over a few hours appears frozen. Stars seem fixed in place. Galaxies look eternal. But in reality, everything is moving. Everything is changing. Clouds collapse. Stars rotate. Galaxies collide. Black holes merge. Matter cycles continuously from one form into another across billions of years. The Tarantula Nebula simply makes those processes easier to see because the scale and intensity there become impossible to ignore. Massive stars flood their surroundings with ultraviolet light so powerful that entire clouds glow visibly across space. Stellar winds carve enormous cavities through gas. Supernovas reshape neighbouring regions violently. The nebula almost refuses to let the universe pretend to be quiet. And still, despite all the violence we explored tonight, there is something oddly comforting about it too. Perhaps because places like the Tarantula Nebula remind us that creation and destruction are not separate processes in the cosmos. The giant stars there will eventually die. But their deaths scatter the materials future stars and planets require. Black holes may form from collapsed stellar cores, while nearby shock waves trigger new star formation elsewhere. Nothing simply disappears. Matter changes form. Energy changes form. The universe recycles itself continuously. Even human beings participate in that cycle. Every atom in your body existed long before Earth formed. The carbon in your cells may once have drifted through ancient stellar atmospheres. The calcium in your bones likely passed through exploding stars billions of years ago. And one day, those atoms will continue onward again. Not dramatically, not poetically, just physically. The same laws shaping the Tarantula Nebula shape everything else too, including us. Gravity gathered gas into stars there. Gravity gathered dust into Earth here. Nuclear fusion forged heavy elements there. Those elements eventually became oceans, mountains, forests, animals, cities, and human thoughts here. The connection is direct. That may be one reason astronomy feels emotionally powerful, even when discussing subjects unimaginably far away. People often assume space feels empty or disconnected from ordinary life. In reality, the universe is deeply interconnected. Stellar evolution affects galactic chemistry. Galactic chemistry affects planet formation. Planet formation affects the possibility of biology. The Tarantula Nebula is not separate from our story. It is part of the larger chain of events that made every living thing possible. And yet, at the same time, it remains wonderfully indifferent to us. The nebula does not know humanity exists. Its stars will continue burning regardless of human arguments, ambitions, worries, or achievements. Supernovas will erupt there whether or not anyone watches. Black holes will form silently inside collapsing stellar cores. The universe does not organize itself around human importance. Oddly enough, many people find that comforting rather than depressing. Because if the cosmos is not centered around us, then perhaps our anxieties are smaller than they feel sometimes too. Somewhere inside the Tarantula Nebula, clouds hundreds of light years wide are collapsing under gravity, while giant stars blast radiation through neighbouring gas at millions of kilometres per hour. Compared to that, forgetting an email or embarrassing yourself in conversation begins to lose a little emotional weight. Astronomy has a way of gently resizing human stress. Not eliminating it entirely, unfortunately. The universe is vast, but taxes still exist. Still, perspective matters, and perhaps the Tarantula Nebula offers one of the most dramatic perspectives nearby. a giant stellar nursery where stars larger than anything humans once imagined live brief, violent lives before exploding and enriching the cosmos for future generations. A region so energetic that astronomers compare it to conditions from the early universe itself, a place where matter is constantly being rebuilt. And through telescopes like Hubble and Webb, humanity can actually watch parts of that rebuilding happen. That remains astonishing no matter how familiar modern astronomy becomes. For most of human history, nobody knew what nebulae really were. People saw faint glowing patches in the sky and attached myths, stories, or navigation traditions to them. They could not know those dim smudges contained stellar nurseries larger than the entire human civilizations by factors impossible to comprehend. Now humanity studies the chemistry inside those clouds. We measure stellar temperatures, masses, and ages. We observe black hole formation indirectly. We detect gravitational waves from collapsed stars colliding across distant galaxies. Tiny creatures living on one rocky planet figured out how to understand events unfolding 160,000 light-years away. That achievement deserves occasional appreciation. And perhaps that is another reason the Tarantula Nebula feels strangely emotional for many people. It represents both the overwhelming scale of the cosmos and the remarkable ability of human curiosity to explore it anyway. We are very small, but we are capable of understanding astonishing things. Tonight, we travelled through one of the most violent stellar environments in the nearby universe without leaving Earth at all. We explored giant stars barely surviving their own light, clouds sculpted by radiation, supernovas powerful enough to outshine galaxies, and black holes born from collapsing suns. And somehow, after all that violence, the universe still managed to look beautiful. Maybe beauty and violence were never opposites in astronomy to begin with. The glowing filaments of the Tarantula Nebula exist because giant stars are tearing surrounding gas apart energetically. The heavy elements required for planets emerge from stellar death. Even the colours humans admire come from atoms being ionized and excited by intense radiation. Creation there is messy, chaotic, dangerous, but also productive. Without environments like this, galaxies would remain chemically simple forever. No rocky worlds would form, no oceans, no life, no observers staring into the night sky wondering where they came from. The Tarantula Nebula represents one stage in the universe teaching itself complexity. And perhaps complexity inevitably leads to curiosity eventually. After all, somewhere on a small planet orbiting an ordinary star, conscious beings evolved from atoms forged in ancient stellar explosions. Those beings built telescopes, pointed them toward a neighbouring galaxy, and discovered giant stellar nurseries glowing in the dark. That is an extraordinary sequence of events, and while the Tarantula Nebula itself will eventually change beyond recognition, the processes unfolding there will continue elsewhere throughout the universe. Stars will keep forming, supernovas will keep exploding, black holes will keep emerging from collapsed stellar cores, galaxies will keep evolving. The cosmos is still busy, very busy. Even now, while you rest quietly here on Earth, giant stars inside the Tarantula Nebula are flooding surrounding clouds with ultraviolet radiation. Stellar winds continue carving cavities through gas. Shock waves keep travelling outward through interstellar space, and because the nebula is so far away, all the light we discussed tonight actually left there around 160,000 years ago. When that light began its journey toward Earth, mammoths still walked across parts of our planet. Human civilization did not exist yet. No cities, no telescopes, no written language. Just ancient humans beneath unfamiliar skies, while photons from the Tarantula Nebula quietly crossed intergalactic space toward a future species that would eventually understand where they came from. That thought alone feels almost impossible, but astronomy is full of impossible things that turn out to be true anyway. And now, as our journey through the universe's most dangerous stellar nursery slowly comes to an end, perhaps you can let that enormous cosmic machinery continue drifting quietly in the background of your thoughts. Clouds collapsing, stars igniting, galaxies turning slowly through darkness, matter recycling endlessly from one generation of stars to the next, the universe carrying on with its vast patient processes while Earth spins gently beneath the night sky, and somewhere very far away, inside a neighbouring galaxy, the Tarantula Nebula continues glowing in the dark,